registered for this, INSYS workshop on applications of electron microscopy for structural integrity investigations. This is the second of the kind that we have initiated for this year. The first was on the digital image correlation techniques, which was an in-person meeting that was held a couple of days ago at the Indian Institute of Science. I think Professor Praveen Kumar, Krishna from IIT Bombay were the resource persons. For this workshop, which is a kind of specialist topic, we have got four the speakers, resource persons. Yeah. They are Professor Vikram Jairam, Honorary Professor from the Indian Institute of Science, Bangalore. Then Professor Shankaran, my colleague from the Department of Metallurgy and Materials Engineering at IIT Madras. Dr. Subir Kumar Bhaumik, who was the former scientist and also a well-known fracture failure analysis expert. And we have Dr. Sundar, who of course needs no introduction. Most of you will know him. He is the the key person dealing with the the BIS ITW, and he is kind of been there in the domain of fractography for more than 40 years, I would say, 40 or close to 50 years. So with this excellent panel of resource people, I'm now starting this program with the first lecture by Professor Vikram Jairam. And for all those participants, if you have any questions, you please type in the chat box. Typically, the lectures are for 45 to 50 minutes, maybe a small plus or minus 5 minutes in some cases. And we will kind of take a few of the questions immediately after the lecture. But if there is a spillover for want of time, if we are not able to take it up immediately after that, we will kind of do it at the end of all the 4 lectures. So please type in your questions in the chat box. And I welcome all of you to this workshop. With this, I hand over the stage to Professor Vikram Jairam.
Yeah, good morning. I hope everybody can hear me. And you can hear me, right? Yeah, okay.
Yes,
so let me just share my screen and start. So I'm going to introduce the subject of scanning electron microscopy. A sense and convey to you a sense of the capabilities of the machine today, and then give you some examples of fracture testing that you can actually carry out inside an SEM. So hopefully this will set the stage for some of the other talks that will describe post-facto analysis of failure, and also the use of transmission electron microscopy in failure. So I assume most people or everybody here has used an SEM. So this is an introduction, assuming that you have used the machine and are familiar with the broad capabilities. So this is the first slide shows you roughly what I will go through, namely what are the capabilities in terms of resolution, depth of field, signal noise, and so on. And then some specialist techniques, which are now fairly routine for high resolution, electron backscattering, and channeling contrast. And finally, I'll end with some examples of in situ testing. So why do we use an SEM? I think this picture illustrates perhaps the primary reason why people use a scanning electron microscope. It gives you enormous depth of field, it requires no specimen preparation, and it is an easy machine to learn to use at a rudimentary level. So the barrier to entry is very low. So what you're seeing here is actually a fracture surface. You just get a pointer. and we are going to successively higher magnification. So this is a 40 micron bar, which becomes a 1 micron bar here, and zeroing in on some inclusion which is present on the fracture surface. So you can see it's very easy to change your conditions. You're seeing a rough surface and you're able to see detail. The reason you're able to do all this is because of the beam divergence and the depth of field. So the beam divergence in an optical microscope at high magnification is almost 90 degrees, the semi-angle. Whereas in a scanning electron microscopes is a fractions of a degree. And that's why the beam doesn't spread very much. And so a region which is in focus here, you can drift away from it in both directions and still remain in focus. So this is illustrated here, where you have a beam divergence of 0.02, which is about a degree. And you will see that some regions are in focus and some are not. But if you reduce the beam divergence, you get a better image. And if you go down to an even lower one, which is 1,000th of a radian, which is about 1/60th of a degree, then you can see the entire field of view in focus. So that's as far as being able to see samples. It was very important in fractography to see rough surfaces, because the fracture surface is generally rough. The next issue is magnification. Changing magnification in an SEM is just twiddling a knob. So here we are looking at this surface here at successively higher magnification. In fact, it's very easy to do, but the point to remember is that you're not getting any information by going to the very high magnifications. Because an SEM does not change the resolution unless you change either the voltage or the beam current. So the detail that you go to a high magnification here, but you're not seeing any detail. In fact, whatever you can see here, you can probably even see in this picture. And there's nothing to be gained. So this is something to remember when you go to high magnification, that you have to change the operating conditions consciously. This is all done for you in an optical microscope. It is not done for you in an SEM. An SEM has tilt distortions. So for example, if this is a sphere sitting on a grid, a square grid at zero tilt, you can see that if you tilt the sample, the sphere of course appears like a sphere, because the projected image of a sphere is a circle, no matter which way you view it. But the grid has become distorted. Now electronically you can compensate by making the grid square, but then you'll notice that the sphere has now become an ellipsoid. So these are some of the things to remember when you look at length scales and look at making measurements, that the tilt that you've carried out is very important, and knowing the axis of tilt. Then comes the signals. The two most common signals, and I will address those here, are the secondary electron signal, which is a low energy electron, typically a few electron volts, and the backscattered electrons, which have something close to the incident beam energy, which may be 10 or 20 kilovolts. The imaging is done through different detectors. Now the secondary electron, being a low energy electron, can actually be deviated. So it can take a very curved trajectory into your detector, provided the detector has a positive bias. So this is why you're able to see inside objects. So this is a nut in both cases. This is viewed with a secondary electron detector, and you can see inside the nut. Whereas for the backscattered electron, it is line of sight. So this region is basically shadowing this lip here is shadowing the insides. Now, the next piece of information you need is, and this is true of any scanning microscope instrument, is what is it that you're sampling? What volume of material are you sampling? And to understand this, we're looking here at a polymer which has been irradiated with an electron beam and then etched in cross section. So this is a light etch, so only the severely damaged region of the polymer is shown, whereas this is a very heavy etch, and you're able to see the maximum extent of the penetration of the electron beam. So the point to remember here is that the region that the electron beam samples is very much larger than the beam size. And it in fact depends on the atomic number. So if you're getting a signal, where do you get the signal from is an important question. And if we look at this slide here, this shows the scattering cross section. So let me just make this a little simple. This is gold, aluminum, and carbon. And the vertical axis is the scattering cross section, and the horizontal axis is the angle of scattering. So remember, to get a backscattered electron, the electron has to turn around by at least about 90 or 120 degrees. So we're looking at this angle here. And you will find that gold is about 100 times better than carbon in terms of the scattering cross section. This means that the signal you get from gold is much higher than the signal you get from carbon. And so this is a function of atomic number, and it's also a function of voltage. So this is, by the way, this is the reason why electron microscope manufacturers will give you resolution standards based on gold, because that's where you get the best signals. You don't get your, so whatever you see in the microscope manual regarding resolution is not necessarily applicable to a carbon nanotube. In fact, it will not. Now, the next thing that you have to remember is this is a very simple formula, and I think it's worth remembering. It tells you the range as a function of the atomic number and density for an electron beam. So there are two parts to this slide. The top part has to do with brightness. This is given for a thermionic emitter. So this is a tungsten filament running at about 2700 K and 20 kV. This is the number of, this is the amperage that you get per unit area and per unit steradian. So this is the number of electrons coming out of the filament. And in a sense, this number limits your signal to noise at the other end. So if you are limited, as we'll see later, we can be limited by the signal because your surface doesn't have enough features. This number can pose an upper limit to how fine a feature you can see, or how little contrast, or what the minimum contrast that you can detect is. The second part is this range of electrons inside the solid. So this is telling you that what you're seeing is not what is a little counterintuitive. And it's not obvious that what you see on the surface in an optical microscope is what you will see in the ICM. And we'll see some examples of that. So this range is proportional to the atomic weight here and divided by the atomic number to the power of 0.9. These two practically cancel out because the atomic weight and atomic number more or less go together. But you will see it's inversely proportional to the density, and it's proportional to the incident beam energy more than linearly. It's about 5/3, 1 2/3 times as the energy. So here are some illustrations of what this means for penetration at 5 and 20 kV for carbon, aluminum, copper, and gold. You'll see the range here is from as low as 0.5 micrometers to less than 100 nanometers at 5 kV, and the corresponding numbers again span about a factor of 6 from the light element to the heavy element. And you will see that in going from 5 kV to 20 kV, you have increased your sampling depth by 10 times. So if you don't want information from underneath, you have to work at lower voltages. Now, the backscattered electron signal, this is what is shown here, is monotonically increases with the atomic number. So this is a form of contrast. Heavy elements will look bright. Now, having said this, there are some details which we don't have time to get into. If you have insulating samples, some of this can be reversed. So we're talking primarily of metals here. So simple comparison of the brightness will tell you whether you have a heavy element or not. For secondary electrons, the situation is slightly different. The depth resolution is exceedingly good because they have very low energy, and consequently they will not escape even though they are generated everywhere. So they may be generated all inside the bulk, but it's only the ones which are within a certain escape depth, which is typically a few nanometers, which will come out and be detected. Now, because the energy to produce these electrons is very low, you can assume that the primary electron, which is, let's say, 10,000 volts, is going to produce the same number in this depth and in this depth as you keep going down, because there's not much of a change in the primary electron energy. Depth of generation, it just goes as a cosine of this angle. That means you get a better signal when you tilt. This is why, if distortions are not an issue, secondary electron images are always taken with some degree of tilt. And this is shown here, where you will see the signal, that is, this vertical axis is the efficiency of producing secondary electrons as a function of the tilt. So this is zero tilt, this is basically 90 degrees normal incidence, and you will see how it increases, both for magnesium oxide and this is, I think, copper or something. Now, where are these electrons coming from? We've seen that there are backscattered electrons which have very high energy and secondary electrons which have very low energy. Unfortunately, the backscattered electrons can generate their own secondaries on the way out. That means if my electron beam is positioned here, I can produce backscattered electrons over a very wide range escaping from the surface, and they act as a secondary source of secondary electrons. So your secondary electron signal is peaked about this point of impact, but has a very broad tail. And this tail is determined by the voltage. So if you go to a low voltage, this tail disappears and you get a signal pretty much from where the beam hits. So this is what I've shown here, that the backscatter yield and the backscatter depth and lateral resolution can limit your ability to even see a secondary electron image. And so your sensitivity to topography is better at low voltages because of this lack of spreading. Of course, the catch here is that low voltages, you get a lower beam current, and therefore your signal gets poorer. Fortunately, with the use of high brightness emitters today, field emission microscopes are now quite common in India. They're more expensive than thermionic sources, but they will be able to allow you to work at very low voltages. Here's an illustration of a fracture surface. This is a hydrogen and brittle fracture surface, taken at 5 kV on the left and 20 kV on the right. You'll see the 20 kV image is brighter, seems to have more contrast, but you actually don't see much detail. These fine detail that you see on the surface is completely lost on the right. That's because your signal is dominated by the bulk, not by the surface. Here's another example of geometric effects. So let's take the top picture here. This is an aluminum copper alloy, which has been heat treated to produce precipitates. Now, these are precipitates on the surface of the sample. So you would normally think of those as artifacts. They are there only because the surface is an easy nucleation site for precipitates. And then there are precipitates at grain boundaries, which go inside the sample. Now, we're going to put two detectors here. One has a high takeoff angle, which means the beam's coming down here and then goes off at a fairly large angle of scattering, whereas this is at a low takeoff angle. The deviation is smaller. And if you look at the two signals, they're very different. The high takeoff angle actually shows you the bulk because it's sampling electrons that have gone deep inside and then come out. Whereas a low takeoff angle shows you all the surface precipitates. This is exactly the same field of view. And this is illustrated again here with a thin film on an alloy. So this is a zinc aluminum eutectic alloy. So there's a eutectic microstructure here, which consists of aluminum and zinc rich phases. And then you have a thin evaporated layer of aluminum on the surface. It's only about 50 nanometers, 500 angstroms here. Again, the two detectors, one shows you only the thin film. What you're seeing here is a microstructure of the thin film, whereas the one on the right is actually showing you your eutectic. So a few more examples of this. Again, the right side is a lower voltage and the left side is a higher voltage. And this is a transistor where you will see there's an additional bright line that comes here at 20 kV, which you don't see at 10 kV. This is a buried interconnect. So it's subsurface. And that's why you only see it when the electron beam has enough penetration. Here are some voids in an aluminum conductor. Where are the voids? Well, these are these voids here. These round black blobs, which you don't see at 10 kV. Again, this is telling you that the voids are buried inside. They are not surface voids. And here's an example of if you wanted to count the number of precipitates on a polished surface, well, you hardly see any at 5 kV and you see a lot of them at 20 kV. So if you're going to do volume fraction calculations, you've got to understand that this has the left-hand picture has the influence of depth. It's really a volume, it's not a surface measurement. What else do you need to get a good image? You need a good dynamic range of contrast. That is, the field of view and your imaging conditions must give you everything from just about where the contrast disappears to something which is full. You don't want to oversaturate and you don't want to undersaturate either. And so this is an example of such a picture. Now, not all samples give you such nice pictures, but there are other things you can do in order to improve your picture. So here's an example where the contrast is very small. So this is the picture. It's a silicon needle and an aluminum alloy. You can barely see the silicon here. So what's done here? The first thing to do is to recognize that there is a signal here. That's what you're getting. That's what you're seeing in these oscillating curves. If you now subtract the DC part of it, this becomes your signal. That is, you just remove the DC component. And now you amplify it. And now you'll get a nice contrast. So this is what's called differential amplification. Now when you do this, you also amplify the noise. So if you've done a bad job of polishing, then all that will also show up. But the point is you get to now see your silicon needle very clearly. Another example of the kind of electronic massaging that you can do, and these are, by the way, available to operators. So you have to find out how to do these things on the machine. Is what's called nonlinear amplification. So here's an example of this is some biological tissue. That's not important at this point. The point is, what is inside this hole is extremely dark, whereas what's outside is very bright. So how do you see both of them? Well, what you do is you amplify one part more than the other. So if you amplify this region more, and that's what the differential amplification does, it's the ratio of the output to the input signal is not linear, but it exaggerates one side. Then you can see that you're able to see detail over here as well as inside this dark region. So this is what's called nonlinear amplification. And finally, we'll come to resolution. Now, this is a busy slide, but I just want you to look at this top equation here. This beam divergence here dictates resolution in addition to the beam current. So we'll just ignore the beam current for the time being and just look at the beam divergence. The lower the divergence, the better your resolution because of aberrations. On the other hand, eventually you'll reach a diffraction limit where the reverse holds. You need a high beam divergence. So this always gives you some sort of an optimal location for your beam divergence. The beam divergence is determined by your aperture size, the aperture through which your beam emerges. In reality, if your contrast is not good enough, you need enough electrons in the beam. And if you need electrons in the beam, you may have to increase your beam divergence. You increase your probe size. That will degrade your resolution. So in a sense, if your feature has high contrast, you can get the best resolution. But if you have low contrast, in order to see anything, you have to compromise. Let me skip this and give you an illustration of the influence of signal and noise. So these are identical, the same sample, but this is taken with a current of 3 picoamperes and this is 10 picoamperes. And this is acquired over 40 seconds, 100 seconds. So you can see there's a ratio of about 3 in the current and another 2.5 in the time. So there's roughly about 7 times more electrons that you've collected here. And as a result of which, you will see that the noise level in the background is much better. You're able to see very fine features here which are barely visible there. So this is and this is why when you take a photograph in the SEM, your typical scan duration is very long. That's how you get the best signal to noise. You can't do it at the frame grabbing rates that you use for normal viewing, which is of course convenient for translating your sample and identifying the region of interest. Here's another illustration. We've said that when the beam hits a particular feature, it produces secondary electrons, which you use to form the image. And so you're able to see some topography here because the number of electrons emitted depends on that local topography. But the beam penetrates inside and can come out at somewhere here and produce secondary electrons, which we call SE2. It can actually hit the hole pieces, the chamber walls, and produce secondary electrons are produced everywhere inside the chamber. And all of these can find their way to the detector because remember they are low energy. So the net result is you're not only sensitive to what you're hitting, where the beam is originally positioned on the sample, but also to a lot of garbage from outside. Now, here's an illustration of what happens if you can eliminate that signal from outside and only focus on or use the signal that comes from the point of impact. So let me highlight one feature here. You'll have to struggle to look at it. I think it looks better on my screen than yours. But here's a point here, which is a small gold particle sitting on this larger gold particle. That is almost invisible on top here. That's because the contrast from this small gold particle does not come only from that particle. Even when you position the beam here, you will get a signal from all around, contributing to it, and therefore the contrast is reduced. Another familiar problem in the SEM is charging. If you have insulating samples or you have samples which are not well connected to your, not grounded, you will see charging. One way to eliminate charging, by the way, is to go to a very low voltage. So this is mica, this is calcite, calcium carbonate. And you will see the artifacts that you see in the image at 15 and 5 kV. It's completely gone, and you're actually seeing the feature, the detail in the flake at 1.5 kV. Charging is sometimes difficult to avoid, and so which is why we coat samples. And here's an illustration of what kind of coating works best. So this is uncoated. This is alumina, this is cotton, and this is polystyrene. You will see the images look terrible. If you coat with gold by evaporation, you get reasonable images. But again, you will see that there's a lot of variation in brightness. This is bright, this is dark, and so on. Whereas if you sputtered gold, which is what we all use. So this is just an illustration of something I hope you all know. If you sputtered gold, then you're able to get a very uniform deposition of your conducting layer. Whereas evaporation is line of sight and tends to miss certain regions in a rough surface. Okay, now briefly on X-rays, because the use of SEM is almost always accompanied by microanalysis. Fracture is always connected to the microstructure, and compositional variations and different phases are always relevant to or play a role in determining fracture paths. Now we have to understand that everything you've learned about so far with regard to the electron beam in the sample has to be repeated for X-rays. And the way X-rays interact with the sample is very different from the way electrons interact with the sample. So here's an illustration of the region that contributes to, this is an aluminum copper alloy. So this would be copper in an aluminum copper alloy, and this would be copper in pure copper on the right. What is shown here are densities of 3 and 10 because these are Monte Carlo simulations. But effectively the density of 3 would be an aluminum alloy with some copper, and the density of 10 would be something close to copper. You will see that the volume of material in which a copper X-ray is produced. So this shaded region is where the copper K alpha X-ray is produced, is different in pure copper than it is in an aluminum copper alloy. This means if you do quantitative analysis, you can't assume that these two are the same. And this is why quantitative analysis in the SEM involves some fairly elaborate software, which is now of course standardized, but it is not simply related to the intensity. You cannot do a direct intensity match and draw any sensible conclusions about the atomic fraction of elements. So this will apply to all elements, and it will depend on voltage. So here's an illustration of the differences between different elements of where your aluminum X-ray signal is generated, not detected, but generated, if the beam were to impact with 15 kilovolts of energy at this point. This is for titanium, this is for copper. You'll see that these volumes are very different. And detection is another story, because an aluminum X-ray has lower energy, its ability to escape the sample is much poorer than that of a copper X-ray. Here is the effect of this of the voltage on the volume. At 30 kV, you get a big signal, but remember it's coming from deep inside. Your point of impact and your beam size may be 1-2 nanometers, but your signal is coming from 1 micrometer. So there is no use pretending that because you use a small beam size that you have spatial resolution for microanalysis. You do not. The only way to convert this into spatial resolution is to reduce your voltage. Because if your beam energy comes down, it loses energy at this depth and is no longer able to produce a copper X-ray. This gives you an idea of length scales for secondary electrons, few nanometers, X-rays of copper K alpha of the order of micrometers, backscattered electrons maybe about 100 nanometers. These are all functions of voltage, so this is done for about 20 kV. Whereas X-rays you can generate, well, it turns out that you can produce X-rays deep inside, tens of micrometers inside. So these length scales have to be borne in mind when you do calculations and get quantitative estimates. Let me quickly come to electron backscattering. You can do crystallography in the SEM. That is, you can detect phases by the crystal structure and grain orientations. So cleavage planes can be identified. You can see whether there are any preferential regions which tend to attract cracks, dislocations, or whatever. And this is the principle of electron channeling. So I'll just briefly describe it because it's quite elaborate. But the principle of electron channeling is the following. If I produce a backscattered electron somewhere in the bulk of the sample, it will have a certain angular variation and vary smoothly with angle. So if I put a very large detector like this, I will get some average intensity varying from bright to dark, spreading over the whole detector. But if my sample is crystalline, on the way out, some of these electrons get diffracted. When they get diffracted by the crystal planes, the intensity reduces in some regions and increases in others. And that is what shows up as a set of these lines. And these bands can be indexed according to the crystallography of your sample. So this allows you to get a lot of information. I've only touched the surface of this, but the point is this technique is now highly developed to look at strain fields, to get misorientations between grains, dislocation densities, and so on. So here's an example of the capability of the software that you have. So this is all done with a click of a button. If you generate orientations, you can then tell the system, show me all the grains which are misoriented by at least 2 degrees. And you will get this color-coded map. So the boundaries between 2 different colors are at least 2 degrees. If you reduce that to 6 degrees, then you find that most of it is one color. And by the time you get to 9 degrees, you have just one orientation. So this is allowing you to determine that pretty much you have a single crystal with a variation in orientation of about 9 degrees. So it is a very powerful technique which very quickly allows you to analyze texture, which can play a very important role in in plastic deformation and fracture. Now, a word on high resolution SEM. This is again routine, but then I find people who don't use it because they don't know it's there or because they can't be bothered. All the detectors we spoke about so far are outside the column. And the distance between the sample and the detector, the sample and the lenses is of the order of a few millimeters, 10 millimeters, 20 millimeters and so on. When you want high resolution images, you go to very low working distances, which means you're so close to the pole piece that your detector has to be inside the pole piece. And the way this is done is to separate the electrons by energy. So the detector detects only the electrons coming out of the sample, either secondary or backscattered, and the optics is configured so that the primary electrons which are irradiating your sample don't interfere. You are now able to work at very low voltages. So let me just quickly run through this. The secondary electrons, which are traveling at a wide angle, tend to, well, they move at a wide angle and therefore they are detected in an annular region. The backscattered electrons have high energy, they don't get deviated by the magnetic field of the lens, and they tend to go straight through. So you can put detectors at different locations, and in addition you can bias them. Remember, if I put a very small negative bias, my secondary electrons will be deterred, they won't be picked up. If I put a slight positive bias, I can attract them. So what does this allow you to do? It's very powerful. Here's a high resolution image. So now this bar here is 100 nanometers. Some of these are catalyst particles, palladium or platinum, heavy elements, sitting in a bed of carbon nanotubes. So this is a secondary electron image, and this is the same image, but with a negative voltage on the filter. So that negative voltage is enough to remove your secondary electrons and only focus on the higher energy backscattered electrons, which you're now able to see with very clear contrast. So you're able to see the platinum particles against this backdrop of carbon nanotubes, which are of course very light elements. And you can mix and match. So this is an integrated circuit. So there's silicon, silica, and various multi-layers here. So forget about all that. But this is a heavy element. This is tungsten. So this is a secondary electron image. You can see the topography of the tungsten here. The backscattered image, virtually no topography. But the tungsten being heavier shows up as very bright. Now you can mix and match. You can take a large amount of the secondary image and a small amount of topography, backscattered, and produce this, or the other way around, principally a backscattered image and a small amount of the secondary topography image. And you're able to see both the atomic number contrast as well as the microstructural features. And lastly, let me come to channeling. And this is a technique which allows you to get image defects directly. So the principle of channeling is similar to what I described in the case of electron backscattering, EBSD. But the principle is the following. If you have a defect, okay, let me just come to the next slide here. If you have a defect, like a dislocation, it bends the lattice planes around it. As a result of which, it turns out that the backscattered intensity follows this variation here because of the lattice bending and the channeling that takes place. Depending on the orientation, the electrons are able to go deeper in and therefore don't get backscattered than in regions where the lattice planes are bent the other way. So I want you to look at this image because normally 20 years ago this would have only been done in a TEM. You can now do it in an SEM. You can image individual dislocations. They show up as bright lines on a dark background. And this is a superalloy. These are gamma prime precipitates, and you can now see the dislocations in these channels. So a lot of what needed transmission electron microscopy has now come to the realm of the scanning electron microscopy, with all the convenience of specimen preparation and, of course, the lower cost. So now let me quickly run through some applications in damage and testing. So this is a picture. Others will show you more pictures like this. These are fracture surfaces, and this is the topography that you're seeing. These are fatigue striations. This is a ductile failure. This is a fatigue crack up to this point, and then an intergranular failure, and so on. You'll see plenty of this. I'm not going to dwell on these very much. Here's an example from a composite. You see the level of detail. These are holes from where the fiber has been pulled out, and so the fiber would actually be on the other mating surface. And here you have a fiber which is broken, which is still attached to this surface here, the one that you're examining. So you will notice that there are features on the fiber surface. This is the fracture surface of the fiber. You can see where the crack nucleated and spread out, and you can see that there's a difference between the propagation here, which is fairly flat, and over here, in the last part of the failure. So all this level of detail, which allows you to, for example, estimate what the starting flaw size in the fiber was, and therefore allows you to estimate the difference between, let's say, two materials, two different fibers made by different processes. In addition, of course, you get quantitative information by looking at the amount of pullout, and these are this data goes into models for estimating fracture toughness. Now, damage is a little more than just fracture, and here's an example from wear. And what I'm showing you here is an example of using focused ion beam machining in combination with the SEM to obtain images. Actually, this image is taken with the focused ion beam. It's not taken with a scanning electron beam. So this is a cross section of a wear surface. This is an aluminum silicon alloy, and you will see that this is the actual surface of a piston, which is rubbing against a cylinder. You will see that the microstructural features here are very different from what it is in the bulk, and this, of course, determines the failure of this material by incremental wear. So this capability now exists to be able to section regions with very high spatial resolution where you want, and then look at damage at very high magnification. The focused ion beam has lower resolution than an SEM, but it gives you much information which you don't get from an SEM with regard to crystallography and different phases. Here's an example from contact damage in a coating. This is a hard coating. So this is a Vickers indentation, and this is a spherical indentation. And this is what it looks like on the surface. But you can now cut this, you can section this material with an ion beam, and then look at the inside. And then you will see that this is your indentation. You can see the curved surface here, and you can see the features, and these correspond to cracks. This is a multi-layer, so there are different phases here, and you can get information on the way in which this coating is breaking, deforming, breaking, and detail, of course, in how the substrate, which is a tool steel here, responds. Here's an example from dwell fatigue in a titanium alloy. So this is a region which is simply shown at higher and higher magnifications. So this region here is blown up in the middle, and it's blown up even more. So what you'll find is a small cluster of somewhat larger grains here. Now, you can do EBSD on this, you can do it on the surrounding region, and you can do it on a cross section. So let me illustrate the detail one can get with this particular instance. So this is the fracture surface, and this is an EBSD map of orientations all along the fracture surface. So this is a cross section of the fracture surface. So I'm looking at it from the side. I can now map the orientation of all these grains. You need a bit of patience to do that. And then plot them in a stereogram. What you find is that there is a tendency for grains near the C-axis orientation, this is a hexagonal material, to break. But the ones that break in conventional fatigue are the ones that have a reasonably high Schmidt factor for slip, so they're not exactly oriented along the basal plane, normal to the basal plane. But in dwell fatigue, the situation changes. So, and these, of course, are inputs into crystal plasticity and other models which try to explain why this phenomenon of dwell fatigue takes place. why cracks nucleate, and they nucleate under certain conditions in fatigue, and if you have a hole at the maximum stress, then the situation changes. So I'm running a little on the late side, so let me quickly go through in situ testing. There's a fair number of examples, but I think you'll get the general idea. The SEM is a powerful instrument for doing testing because it has space, and there are now experimental arrangements available that allow you to do a test inside and watch what happens. And so this gives you information at very small length scales where you can combine microstructure and fracture measurements. This is an example from silicon. 4 different types of tests which give you load displacement curves while the test is going on, and this allows you to measure K1C. So now I'm talking about the SEM is used for not post-facto analysis, but actually making toughness measurements. Let me just exit here and show you something else. This is an in situ fracture test. I hope people can see this movie. Can somebody say yes or no?
Yes, yes.
Yeah, okay. So this is a load displacement curve, which is coming from this. So this is a wedge which is being used to deform this beam where there's a pre-crack. So this is a fracture toughness testing geometry. So you're getting a load displacement curve, and I'm going to speed this up and you will see that the crack now starts to extend. You start getting non-linearities in the load displacement, and you will see the crack extend now. So you can map the position of the crack to the load. I'm just speeding it up, and then you can unload, of course, and go back. You can repeat this process. So what has this given you? You basically R curves. So you can measure these R curves, and the reason we do it in an SEM is that the sample is very small. It's a coating. So the entire thickness of the sample is only 20 microns. So you can see the crack here moving, and at successive positions you can obtain the loads and therefore measure toughness and obtain resistance curves. You can do this in fatigue. So this is a similar material. This is the original notch, and you will see that when you do the test, these images are from a TEM, they're not from an SEM, but the test was done in an SEM, and so the data these load drops give you the point at which the crack is jumping forward. So these are very low velocities. The crack velocity here on average maybe 10 to the 9, a few nanometers per cycle. But it happens in jumps, and you can now catalog where these jumps happen. It basically jumps, stops at a grain boundary, renucleates. Sometimes it follows a cleavage plane if it's available. If not, there's branching and so on. And then you can see the collateral dislocations that are produced as the cyclic loading takes place. Here's an example of measuring fiber matrix interfacial strength. So this is a region cut out using a focused ion beam where we know that the interface is at an angle. So if you load this from vertically, from the top, you're putting this whole sample in compression, but the interface is now in shear. And so the load displacement curve gives you the interfacial shear strength. Here's an example from hydrogen embrittlement. So this is a sample. Again, this is a cantilever, so this is a pre-crack, and you're looking at the degree of blunting. So this is a very sharp crack. Propagates is a sharp crack. Here, there's blunting and a lot more dislocation activity. Then, by the way, that comes from EBSD measurements. So the electron backscattering is telling you the effect of hydrogen charging. When you have hydrogen charging, you have much more brittle behavior than if it's hydrogen free, where the displacements are much larger and the degree of the toughening and the blunting of the crack is significantly greater. Here's an amusing one. It actually was published in Science. How does a razor blade cut hair? That we know, because a razor blade is sharper than your hair. But how does a razor blade get damaged by hair? This is something which is not very obvious. So this is an experiment done in an SEM to show how, this is the hair here. I don't know, do I have my pointer? Let's get back to the laser pointer. This is the hair, and this, you're tracking the movement of the, I think they move the hair. And this is the razor. So at the end of this process, you will see 2 nanometer scale chips formed on the steel surface. So they have a theory for how this happens. But the point is, you can now actually monitor the way in which damage accumulates in situations that you wouldn't have dreamt of doing earlier. And these are the level of a few nanometers. These chips here, of course, this is 75 microns, but the chips start off at the level of a few tens of nanometers. The coupling of EBSD and digital image correlation and SEM is again a very powerful technique for looking at fracture. So if you have features that allow you to do digital image correlation, then you can see things like persistent slip bands, and that's what is shown over here. This is a superalloy which has gone through some sort of a cyclic loading, and you can see these slip bands emerge and disappear, and you can distinguish the ones which are reversible and the ones that remain. So over a period of time, you can actually track the failure, eventual failure after thousands of cycles, to certain slip bands that originated at the beginning. So you know which ones actually led to failure, and the others were simply going back and forth and underwent reversible behavior. Monitoring ductile brittle transitions. So here's an example of the level of detail that you can get from an in situ experiment. If you do ex situ experiments, you find that this material is brittle up to 700 and then is ductile at beyond 700. If you do in situ experiments, you can actually track the toughness and see the slow transition, which then abruptly increases beyond about 600 degrees. So this is in silicon, and monitoring of plasticity and crack branching and so on during in situ measurements. This is an example of R curves in nacre. So these are biological bioinspired materials, or this is actual nacre, where you're looking at cracks emerging from a notch. You can make displacement measurements, you can determine J integrals and so on, and you can do the same measurements at this microscopic level. By the way, I'm cheating. This is not an SEM picture, it's an optical micrograph, but the point is you could do it in an SEM as well. You could do the sort of things now that you would be unable to do with traditional COD gauges and so on. So I think I'll stop at this point. This is one more example. This is wood. So the site-specific capability of microscopic testing in fracture allows you to see different regions. So wood itself, we think a tree is a tree is a tree, but there are different kinds of wood depending on when it's grown and whether it's in a branch which is put into compression or in tension. The mechanical properties of wood are different. So that's what's called normal wood and compression wood. So one is able to go to selected regions, machine samples out, again using a focused ion beam, and determine average ductility. So you can see that the load displaced stress strain curve here goes out to about 50%, whereas here things break around 15%. So this is the level at which one can carry out experiments in the SEM. So I'll stop at this point, and I hope I've given you a sort of a broad introduction to the capabilities of an SEM and the factors that you must learn to control so that the images are readily interpretable, and then some examples of testing inside an SEM. So I'll stop at this point. If there are any questions, I'll be happy to take them.
Thank you, Mr. Vikram, for this nice lecture. I think many of us are using the electron microscope just like the way we use a car, but we don't understand the basics of it. As a consequence, sometimes we don't extract the best out of those measurements. So your talk, brought out all the significant points. I will just see if there are any questions in the chat.
Raghu, I'm looking at the chat box. Can I just run through them?
Yeah, please.
So the first question is from Monica Bhagat, CNTR. Sorry, lost that. Yeah, it says features, pillar and size is changing in every angle. How to do tilt correction? Yes, this you have to know the tilt. You have to know the angle of tilt. So these are now automated. So when you do focused ion beam machining, and then you view it at an angle which is governed by how much you tilt, those things are fed into software which will then tell you how long the actual pillar is. But typically when you do testing, the pillar is vertical. It's only when you do imaging that you may tilt it. The next question from Deepa Srinivasan, could you please throw some more light on in-lens mode versus low working distance? So the low working distance up to about 10 mm can, maybe 10 mm, yeah, can still utilize the detectors which are in the chamber. But once you get lower than that, these electrons leaving the sample cannot cannot be collected by those detectors. It's too close to the pole piece. So now you have to use the in-lens detectors. So there's a facility in the machine to choose in-lens detectors. You would choose that at working distances of 3 mm, 2 mm, and so on. Two queries about EDS from Sandeep. What should be an optimized condition to identify following on a fracture surface through oxidized layers, and secondly through reliable identification of surface precipitated particles? Okay, just a general thing about thin layers and particles. All the software that you use in the standard software that comes in an SEM assumes that your surface is flat, and it assumes that the composition is the same within that region, the affected region from which your signal is coming. So if you see a 10 nanometer precipitate in a matrix which is obviously larger, you cannot get quantitative information on the precipitate. If you have a particle, you cannot get quantitative information on the composition of the particle because it is a round surface and not a flat surface. There are corrections you can apply, but it gets more elaborate. So if you have a thin film on a substrate, you have to estimate whether the penetration of the electron beam is sufficient to excite X-rays from the substrate. You can work at low voltages, but if you go to a very low voltage, you won't produce the X-ray because you need a minimum energy in the electron beam to cause the ionization needed to produce the X-ray. So these are all the compromises. Instead of a K, you can use an L and so on. But broadly speaking, the analysis you do is qualitative. It tells you certain elements are present, and if the features are very small, you have to use other information to guess what your precipitate is. I mean, if you know that it's a superalloy and or let's say it's a steel and it's a ferritic steel and you have chromium and carbon, you can draw some conclusions that it's a chromium carbide. But whether the carbide has iron is more difficult because there's iron that's coming from the matrix as well. How do we achieve differential amplification? This is from Abira Rashid. Differential amplification practically in an SEM. It's there. You have to go and look into every machine has its own, operating manual and they're often not called exactly the same thing. I'm afraid I can't tell you where it is in your SEM, but go and ask the operator and dig in a little bit. So question saying how to improve differential amplification at tool. I'm not sure I understand what that means. But basically differential amplification consists of removing that background and amplifying it after after removing the background in order to get contrast. Again, there's a limit to how much I can answer in a video seminar. These kinds of aspects have to be done on the machine to understand the procedures you carry out. How to decide the contrast in backscattered SC for our specimen, say metals, titanium. Again, I'm not sure I understand the question, how to decide the contrast. If you have a titanium alloy which is single phase, there's nothing to see except different grains. Now to see different grains, you have to etch the sample so that different grains are revealed. If you don't want to etch the sample, you have to use electron backscattering. So you can get backscattered contrast, which is sensitive to orientation, and that would be a way of measuring grain size. If you have two-phase materials, then you carry out the same process you would do in an optical microscope. You etch the sample to reveal them. If you don't etch, then you're relying on compositional differences to see them, and that contrast is poorer. Topography is always preferred as long as it doesn't interfere with other experiments you want to do. Srinivas Prakash says, I got very neat SEM images for ABS polymer, but faded ones for Inconel. Does it point to oxidation of the Inconel? See, when you say neat images, it depends on what information you're getting. If you have topography like you have particles, you will get neat images. Whereas if you have a polished metal surface, you will see nothing. So again, the question is, what features were you expecting to see? If you're expecting to see grains and precipitates, well, it depends on whether you etch the sample at all. If you didn't etch the sample, then you're relying on atomic number. And there may not be sufficient differences to see them very easily. I'll run through these quickly. What is the approximate starting range budget for, for an SEM? This is like asking what car to buy. This is from Karthik Srinivas. I suggest you ask what the money available is and then see what can be bought. A field emission SEM, I think the basic machine will be about $250,000 to $300,000. And then you start adding attachments like EBSD, EDS, and so forth. A thermionic machine you can get for cheaper. And if it's a tabletop machine with limited capability for undergraduate classes and so on, you may be able to get it for about $50,000. Okay. Yeah, Raghu, we'll do the others later because we're running late.
Yes. I'm really sorry to interrupt on this
question
and answer sessions. I think we will thank Professor Vikram Jairam for this excellent lecture. We have 3 more lectures following this, so I have to keep track of the time. So please bear with me. And thank you, Professor Vikram Jairam, and we will kind of give a round of applause.
Thank you.
Electron through the online mode. So thank you. I think you can unshare. Now, the next talk.
I'm unshared.
Okay, good. Thank you. So the next talk will be by Professor Shankaran from the Department of Metallurgical and Materials Engineering, IIT Madras. He will speak on the studies on the damage accumulation in single and multi-phase steels during strain control fatigue using transmission electron microscopy. I must confess that I'm not introducing the speakers like what they do in a typical workshop or a seminar for want of time, and I believe all of you know the speakers so well that I don't need to introduce them. If you have any questions, you can just type in their name on Google. You will get to go to their web page. So, Professor Shankaran, please start your presentation.
Thank you, Raghu Prakash, Professor Raghu Prakash. Can you all hear me?
Yeah.
Is my slide visible?
Yes,
Yes, sir.
title slide is visible.
Yeah. Thank you, Professor Raghu and Vikram for asking me to do this, and I'm happy to present some of our old results, what we have done using transmission electron microscopy. So my lecture will be slightly different from what Professor Vikram showed, because this is going to be kind of a research seminar. But then Professor Raghu asked me to give some introduction about the TEM. Then the total time available for my lecture is about 45 to 50 minutes. Then I thought I will give some introduction, but Vikram also warned me if I'm able to do some introduction for TEM in 15 minutes, how it will be. But thanks to Professor, Nestor, who came to our institute and gave some nice slides. So I thought I will introduce the basic imaging techniques of TEM, through which we have characterized all this post fatigue tested samples to understand the deformation mechanisms and so on. So my talk will be on the studies on damage accumulation in the single phase austenitic stainless steel and multi-phase microlloy steel during strain controlled fatigue using TEM. So let me just introduce some basic imaging techniques in TEM, so that that sets the stage for what we have practically doing in post-tested samples. So all of you know that TEM, if you can look at the electron optical systems, and then you've just shown this comparison for the optical microscope, and you have the electron gun, and which you can extract the electrons and accelerate through the column with all magnetic lenses like this, and then you can just connect the 1:1 almost the condenser lens and objective lens and intermediate lens and projection lens and so on. So that the electron optical system, the optical rules are almost similar to what we do in a light optical systems. So this is just this image clearly demonstrates how these electron lenses are in correspondence with 1:1 with an optical systems. And what I'm trying to show here is the ray diagram which go through the column. In TEM, typically the parallel beams are used, and the image, especially for an imaging, you can use parallel beams, and the electron beam pass through the specimen, and then you have this objective lens. You can use these two column ray diagram shows, one is for diffraction and the right hand one is imaging, but I just show you what kind of apertures and then change in strength in the lens current. I just compare these two. For example, if you want an image, then you use, you don't change the objective lens current, but you change the intermediate lens current so that you keep this lens here in this image plane, and the objective aperture is in the back focal plane. And then the images are further projected or magnified with the projector lens, and then you get the final image. On the other hand, if you are interested in the diffraction information, then you change the lens current, and then you look at the image plane and using this SAD aperture, and then what you see is what we are looking for is a diffraction pattern from the back focal plane, and then the projected lens further magnifies this, and then you get this finally a diffraction pattern on the screen. So this is some of the very basic ray diagram which a TEM uses, and I'll just show that a cross section of the total column which is open. We can see that the electron gun and then all the magnetic lenses, and then you see the stages and where the sample is inserted with other detectors are there, and then you have the projection lens, and then finally you have this fluorescent screen which you can see through this binocular. So this is just give you an idea. I mean, what is that which I showed in the ray diagram, and then practically what you see in this microscope. So now I'll just briefly introduce the diffraction. I mean, the imaging techniques basically. In TEM, basically you have, the image which gives the contrast through three mechanisms. One is amplitude contrast, and another is diffraction contrast, and there is a phase contrast. So the amplitude contrast is mostly deal with a low magnification imaging, something like this. And then diffraction contrast, primarily we use it to understand the defects like this. And then you have the phase contrast, which gets, we study the lattice information and so on. So we are, in this, I will talk only about this conventional TEM imaging technique, mostly amplitude and diffraction contrast, which is primarily used for most of the cases. So if you look at the major factors affecting the TEM image contrast, you have, you have the thickness, where you have the differential thickness of the specimen. So based upon the thickness, the scattering of the electrons by the specimen varies. So that creates a contrast here. And second one is an atomic number contrast. So the more higher the atomic number, the scattering power also is different. So that creates a contrast. That's atomic number contrast. These two are basically from the scattering of electrons. And the third one is the orientation contrast, depending upon how the planes are oriented with respect to the Bragg angle. So that decides the contrast, or whether you are able to collect them through the aperture or just diffract away from the optical axis. That decides the contrast. So that is called the diffraction contrast. And then you have a defects contrast, which uses both scattering and diffraction. So these are the major factors affecting the TEM contrast while imaging. So just give some examples. Whatever the contrast mechanisms I just spoke, they are all elastic scattering. So the amplitude or mass thickness contrast basically arises from the varying mass of the specimen attenuates the beam. So as I just mentioned in the previous slide, it creates a contrast. On the other hand, if the diffraction contrast, basically the orientation of the specimen, especially with respect to the plane which diffracts, whether it is passed through or it is just go away from the optical axis, or if it's going out of the aperture, that creates the contrast, basically a Bragg diffracted beam or escaping from the optical axis, then that creates a contrast. On the third one is the phase contrast, which is basically an interference phenomenon of the scattered beam, whether constructively or destructively interact with each other. So that creates a contrast, basically the phase shift of the transmitted beam and the diffracted beam. Each one will have a different phase shift, and by interfering these two transmitted beam and the diffracted beam interfering continuously produces a differential in phase contrast, which is also you can see it in a simple optical microscope. Also, we have the phase plate which shows the phase contrast. Similar principle is used here as well. But when you talk about inelastic scattering, which also Professor Vikram talked about all the elemental analysis in SEM, like SEM, we have a TEM, also we have in EDS. We can produce all the, which uses inelastic scattering to identify all the chemical information in the much lower scale. So that's one difference. if I just talk about the contrast, first let us talk about the mass thickness contrast or atomic number contrast. What I am trying to show here is the contrast which is appearing in an amorphous solid. So the intensity, what we are just looking at here, is nothing but the square of the atomic scattering factor times the periodic function, which is related to the angle and the nearest neighbor in the lattice. And basically what you see here is the higher the thickness or higher the atomic number, the scattering will be at a much higher angle. Suppose if you take a cross section of this diffraction pattern, what you show here, you will see a profile like this, something like this. So the higher the atomic number or thickness will diffract at much higher angle, which will escape from this. So typically, if you put an aperture here in the center, all the higher number will escape, and then that will appear, those regions will appear dark, and the electron beams which are able to penetrate through are lower atomic number or lower thickness, they will all appear as bright. So this is a typical mass thickness contrast in an amorphous solid. And what you can see is, so if you look at the ray diagram for this, it is nicely shown here. Basically, what you are looking at is you have the sample, and the electron beam is considered as a wave here, so which comes out. So the intensity is nothing but the complex, product of psi and the complex conjugate of that, and then you have the initial I naught initial intensity times exponential factor of a cross-section coefficient times the thickness of the sample. So you have the beam which is coming through the sample, and then you can see that the aperture is just blocking all the diffracted beam, and then you will use only the transmitted beam. So that creates amplitude contrast. Okay. So basically, the amplitude contrast, the first approximation images the unscattered beam, and typically an aperture is used to permit only the directly transmitted beam, like I just showed in the previous slide. This is an example where it shows the biological tissue, how it creates the contrast. You can see that a dark contrast and a gray contrast and a bright contrast, depending upon where the electrons or the scattered beams are collected, they'll all appear bright, and which are all escaping, the aperture will appear dark. Or if it could be also a thickness variation, then you will get this kind of dark, gray, and bright contrast. So next to the diffraction contrast is again, you can see that the intensity is, earlier we are talking about the atomic scattering, square of the atomic scattering factor. Now it is a structure factor, and which is from the whole unit cell or from the whole lattice. You can just summation of individual atomic scattering factors times the periodic function, which is given here, which all you would have studied in the X-ray diffraction course. The similar, the concepts are similar here. And what you are seeing here is a bright field image. So you have a bright region and a dark region, and then there's a hole. So the hole will appear bright because the beam penetrates through. And here you have a brighter region because most of the electrons are able to penetrate through, because the crystal is oriented in such a way that all the scattered beams are able to penetrate through. But some of the regions, for example, this boundary, after that you have the dark region. That means the diffracted beam are escaped from the optical trajectory. I mean, the sense objective apertures. Basically, they escape the objective apertures. They are all removed from the optical trajectory, so they are appearing dark here. And what you are seeing here is again a dislocations, like Professor Bikram showed that, when a dislocation is there, that the lattice planes are bent, and if the bent planes are oriented in such a way that they are Bragg diffraction, enabling Bragg diffraction, and then they are escaping. That's why they are appearing dark here. But the other regions, you are seeing that the electrons are able to penetrate through. That's why it is appearing bright here. So that creates a kind of contrast. So typically a diffraction contrast is studied like this. So same thing, information, what I just mentioned in the previous slide is shown in the schematic here. So you have the dislocation and the bent, the planes around it are bending, and which are Bragg diffracted, and then they just escape the apertures, and then that produces a contrast. So basically, this is the ray diagram for the bright field imaging, where you have the direct beam comes through the objective lens and then the aperture, and then all the diffracted beams are stopped. So that's how the contrast is created typically in the TEM in a defects or grain boundaries and so on. So you have basic imaging techniques in TEM. One is bright field imaging, another is dark field imaging. In a bright field imaging, you use a direct beam. So you have a typical, the background will be brighter, and all the other features appearing dark because they're all stopped by the aperture. So this is, suppose if you are interested in a dark field, you can use any one of this diffracted beam based on the interest, and you can see that typically the dark field image appears like this, where it clearly captures the precipitation on the grain boundaries, and then more fine precipitates on the matrix. So you can see that the electron beams are exactly diffracting. That's why it is appearing dark here, and here it is bright because you are able to capture that diffracted beam here directly. So similarly, you can look at a different diffracted beam, get the different information of probably this, some other plane will show up in the other diffracted beams and so on. So this is a basic imaging technique in TEM. And then there are other two phenomena in TEM imaging, is like one is the bend contours, another is the thickness fringes. And if you can understand these phenomena by the kinematical theory, which expresses the intensity of this by this equation, which is related to, again, a sinusoidal function, and it is also related to thickness and the orientation. Okay, so you have the thickness, basically a wedge, a thickness varying continuously in the sample. Then again, the beam try to oscillate in this manner, and this is this is shown here in the schematic how the oscillation happens. And practically, what you see is the oscillations will smeared out as the thickness increases. Okay. And similarly, it is shown for the amorphous solid. What you are seeing here is the intensity is expressed in a similar manner. Like it's also related to something called extinction distance. So that is nothing but related to the periodicity of the intensity oscillation, which is also a characteristic of each material. So most of the standard textbooks give the extinction distance of various materials. By just looking at the counting number of fringes appearing, you will be able to estimate the thickness and as a rough estimate. But it is easy done than it's very bit involved, but it can be done. So that is about this thickness fringes, and then bend contours is the same. Nothing but there we are talking about thickness variation. Here it is orientation. So you see that the sample is bent here. Again, it is expressed by the same intensity equation, and which is nothing but here. There we are varying the thickness. Here we are changing the orientation by the bent sample. So these bend contours, how to distinguish, then if you just tilt the sample, they'll all move all over the place. So they can identify them much easier compared to any other defect features in the material. So the last contrast which I am talking about is a phase contrast, so which is, as I just mentioned, it is an interference phenomenon between the transmitted beam and the diffracted beam. So here, if you remember the initial equation, I just stopped with the first term, and then now it's going to have several terms because it's going to, the number of terms is going to increase as the interference between this transmitted beam and the diffracted beam. So you can keep on increasing the number of beam interaction by opening up the aperture. You can allow as many beam to interact, and then these terms will also increase. So basically, this particular contrast mechanism is, used in the interpretation of the lattice fringes and lattice imaging, which I'm not going to show the examples here. I just mentioning the difference between the diffraction contrast and the other mass thickness contrast and so on. So what I'm going to just show in my case study is basically a conventional TEM, which I have used a diffraction contrast. We try to study the especially fatigue samples. Okay, so the project was to optimize the nitrogen content in 316Ln stainless steel for enhanced low cycle fatigue life. So I'll just go through this. So we just looked at the cyclic deformation behavior, and we also looked at other fatigue interaction. I'm not going to show all of them, but at least what I'm interested to show here is the substructure developed during the low cycle fatigue, and then we looked at whether it is a planar slip mode or a wavy slip mode or a mixed mode, and then we just compared them with the fracture and fatigue life and so on. So the major mechanisms which is operating in this particular stainless steel, here we have the dynamic strain aging and the secondary cyclic hardening and the cyclic strain induced precipitation. So these three aspects are well captured in this study that I just want to share. So what is why 316Ln? Because it is used in the sodium cooled fast breeder reactor. It was a project from IGCAR. We had studied this, and this material is used for main vessels and inner vessels and primary sodium pump and so on. So the idea is to reduce this section thickness from the viewpoint of magnitude of thermal stresses and cost reduction and so on. So, and we also understand that the high strength can be achieved by the nitrogen alloying in this austenitic stainless steel, and so that it can be used for the future commercial fast breeder reactors in India. So what nitrogen do? I mean, nitrogen introduces a planar slip in a material, and the idea is which is beneficial for the slip reversibility and then fatigue endurance. So this is the bottom line with which we added nitrogen, but at a different content. But how much nitrogen is beneficial? That was the question. So that's what we try to optimize in this study. So if you look at what is planar slip and what is wavy slip. So if you have the schema, if you look at the schematic, so all the dislocations will try to glide in a same plane, and which also will form as a fine slip band in a failed material or under microscope. You can observe them, and basically, and then wavy slip, you have the dislocations will move all over the directions, and it will not be of a planarity. So you have it will create a coarse slip band as compared to the planar slip band. So the slip, if you have the slip irreversibility, then the localization of strain happens immediately, and then which is detrimental for the fatigue life, and then because the specimen fails much early. On the other hand, if you have the slip reversibility, which is beneficial because it delays the crack nucleation during fatigue. So this is an idea. So if you look at what the cyclic response, stress response of this material, it's quite interesting to see that this is a room temperature stress response, and what you are seeing here is at high temperature behavior. So this is actually a reverse temperature effect what you are seeing, because you see that higher the temperature of operation you have, the strength goes up, and also you see that kind of a hardening takes place towards the end of the life. So these two phenomena are because of the dynamic strain aging as well as secondary cyclic hardening. But what is this nitrogen doing in this material is, like, if you see that at lower concentration of nitrogen, it creates a kind of cell structures. Okay, so and then as the nitrogen content increases, you can see that a planar array of dislocations which creates here. So nitrogen addition enhanced cyclic softening at room temperature, so which is evidenced by this creation of nice dislocation cell structures in the matrix. And at the higher temperature, a partial or complete offset of cyclic softening. So that you can see it here. So the high temperatures, it is completely offsetting the cyclic softening because of the dynamic strain aging. But does it happen in all temperature at all strain amplitude? That is something which we have to decide. That's the idea of studying this. So if you look at the dynamic straining aging effect, we know that this is because of the interaction between solute species and mobile dislocations in the material. And this particular DSA temperature region encompasses the service temperatures, which is about 350 to 550 of many sodium reactors. And this phenomenon causes a high degree of initial cyclic hardening at the extending over the number of cycles. Right? So what you see here is this is stress response is greater than 0.6% of the amplitude, and this is less than 6%. So it happens only at the particular strain amplitude, which is, you can say that DSA is observed to be significant only for the total strain amplitude less than or equal to 0.6%, which is shown here. For the strain amplitudes greater than 0.6%, you can see the high propensity of cross slip overrides the planar slip due to the DSA and cell structure formation. So you can see that at 0.4% of the total strain amplitude, you can see that the planar slip. And if you just zoom in a little bit on these slip bands, you can see that the dislocation array in a single, they're all arranged in a single plane kind of thing, planar arrangements. Okay, but on the move to higher strain amplitude, you can see that the planar slip activity goes, and then you have started seeing the dislocation walls, and then finally the dislocation cells. So the message is the DSA phenomenon is quite prominent or significant only at 0.6% of the total strain amplitude. So we just looked at the fractured surface, how this DSA is affecting this. So wherever you have the DSA happening, so the localized deformation and matrix getting hardened, and then shortens the crack initiation and propagation periods. So DSA also increases secondary crack density with the increase of temperature in DSA. This is what's shown here. So you can see that as the temperature increases, you can see that the crack density is also quite significantly increasing. So significant reduction in fatigue life in the DSA temperature region between these two, this range, so which is detrimental for the LCF life as far as this particular material. See, if you look at the secondary cyclic hardening very closely, what you are seeing here is the material tested at 0.25% of total strain amplitude at 773 Kelvin. So you can see the signature of secondary cyclic hardening towards the end of the life. So as the increase the nitrogen content, you can see that more and more hardening effects are seen here. So similarly, you can see that it's the DSA effect and combined with the secondary cyclic hardening. So we are kind of mapped all the temperature and nitrogen content and the total strain amplitude. You can see that the more the nitrogen is in the material, the secondary cyclic hardening is pronounced more here, especially at the low strain amplitude here. Okay. So the deformation substructures reveal the planar mode of deformations evidenced by the planar slip bands containing planar slip dislocation arrays dispersed with dislocation dipoles, multipoles, small loops, and dislocation pairs. See, we just try to see all these features under the TEM. So this here it is, especially the region where we understand where the beginning of the secondary cyclic hardening. So you can see that the slip bands are like this, and then this is the grind boundary. And these slip bands, if you just focus a little more on this, you have the dispersion of dislocation pairs and small dislocation loops. All of them could be identified, and you can also see some of the multipoles and dipoles, which are all act as hard particles. In fact, they will act as hard particles in a matrix. And then you can see clearly that this is the beginning of the secondary cyclic hardening, this is the middle of secondary cyclic hardening, and this is an end of secondary cyclic hardening. Okay, but this is for the 0.14% of nitrogen, but as the low nitrogen, you don't see these kind of planar activity. Okay, and also if you this is tested at 0.6% of total strain amplitude, and this particular results clearly demonstrates that it is the nitrogen. A small increase in the nitrogen creates quite a bit of change in the substructure formation as well as the fatigue life and and the endurance. So this slide kind of summarizes what you can see in totality as a function of nitrogen content and as a function of total strain amplitude of the testing. So you can clearly see that at low strain amplitude, you don't see that planar activity, but with increasing nitrogen content, you can see that the planar activity is increasing, and high density of planar array of dislocations you are able to identify. And if you go down from the low, just for this given nitrogen content, if you increase the testing amplitude, you can see that the transformation is from dislocation bundles to elongated dislocation cells to dislocation cells. This is very nicely shown here. And then if you go from the higher nitrogen content and higher strain amplitude, you can see that how the planar arrays of dislocation is transforming into slip bands and very closely, and then you finally form unidirectionally aligned dislocation walls as compared to what you see here. So this is a clear indication of the nitrogen effect, and these substructures directly related to the strain localization and the crack initiation and so on. This is what we have just summarized in the table. Like you have a mixed mode of damage accumulation happens here, and then you have, as the nitrogen increases, content increases in the material, the material experience primarily a planar mode of slip, and as you go in across, then you have a mixed mode, and you see that what we have seen here. But when you do it at high temperatures, and there is another variable which is coming in, the grain boundaries have started giving all the decorated precipitates, which is M2366 here. So this is kind of a cyclic strain-induced precipitation of carbonated grain boundaries, and this will also have a significant influence on the fatigue life and strain localization and so on. So what you are comparing here is the influence of nitrogen content on LCF life. So you can clearly see that based on the substructures and the data, what you are seeing is at low strain amplitude, there is an increase in secondary cyclic hardening tendency with nitrogen, and life decreases with increasing the nitrogen content. At 0.4% of strain amplitude, increase in planar slip activity, and then LCF life increase with increasing nitrogen. But on the other higher strain amplitude, you can see that the planar slip, including the planar slip and impingement of grain boundary precipitate at highest nitrogen content. So which is further deteriorates the fatigue life. So we are trying to relate this, macroscopic fracture mode and microscopic deformation mode at high temperature. So what you are seeing here is a replica taken on the fracture surface, and then we try to correlate this with what the substructures we are seeing in the post-tested material. You can clearly see that all the crack propagation path, these particular regions correspond to, you have the planar arrays of dislocations, which is of high density. Okay. So again, you have the replica for the higher nitrogen content, and you can look at the test conducted at the very high strain amplitude, also correlated with the kind of grain boundary which are decorated with the rich carbides and the slip bands, and then the kind of dislocation cells which is generated. They are all corresponding 1:1 almost with the fracture features. So the increase in the strain amplitude from 0.4 to 1%, then the transition from transgranular to intergranular crack initiation and propagation. And the drastic reduction in life at highest amplitude is also evidenced because of these events, microstructural events. So you can also look at the microstructure evolution as the function of plastic strain amplitude. Basically, if you look at this, all the strain amplitude what we have tested, and then it also shows a single slope and a prominent wavy mode of deformation for the strain amplitude, which is greater than 0. So this planar slip activity happens primarily less than this 0.25% of strain amplitude. And then this, you can see that the corresponding substructure development, which is nicely correlated. It is a similar thing here with other nitrogen content and so on. So if you look at the total strain life plots, which is all summarizes the whole thing, which is a dual, which the material exhibits a dual slope at 773 Kelvin and 823 Kelvin, and change in deformation mode from planar to wavy at amplitudes greater than 0.6, which is what we have shown. And single slope behavior at 873, prominent wavy mode of deformation at strain amplitude greater than 0.25. Okay. So these particular, based on these substructures, we come to an optimal nitrogen content, which is good for this material. And we also recommended this for their design aspects. I just show what is that we have concluded based on this substructure development after the fatigue testing. So you have this the concepts which are happening based on the dynamic strain aging, precipitation, and creep and oxidation. So you have, if you have the low nitrogen content and then you have these kind of transgranular fracture, and then if you have the nitrogen content which is less than 0.1, then you have this kind of mixed mode of intergranular fractures. So based on this studies and other substructures, we come to a conclusion where you have an optimum nitrogen could be between somewhere 0.7 to 0.11. So the conclusion, the major conclusion is the nitrogen in 316Ln stainless is beneficial for improving LCF life. The failure is only by the transgranular fracture, and is detrimental if the failure includes considerable intergranular damage component. So you can see that the substructure detailed study gives much closer look at the critical concentration of nitrogen in deciding which is better for this application. So that was my first case study. Then I'll just show another interesting case study in a multi-phase steel. So this will be a little more complicated because what we have just looked at is much straightforward. It's a single phase material. But this is also an interesting study because this was studied, during my PhD. Then I just continued to look at the microstructure development because it was so complex to understand. So, but at the same time, it was challenging, and to get a correct interpretation on what causes the stability, right? The multi-phase steels showed extraordinary stability under the strain-controlled fatigue. So the challenge was to understand what happens. So even a single phase, when it develops kind of substructures, you have seen that it is too complex to interpret. But in a multi-phase like this, where you have all sort of martensite, bainite, and polygonal ferrite, and so on, retained austenite. So the microstructure is pretty complex, but the properties are interesting. What you are witnessing here is the cyclic response. You can see that up to 0.6% of total strain amplitude, the material exhibits almost steady state till the failure. So this was quite a interesting LCF behavior. So we try to investigate through a post-tested material under using conventional TEM. So this is the heat-treated microstructure, which is, I'm not giving too much of details here, but I will just mention the details while I just show the deformed structure. So basically the microstructure contains the non-equilibrium phases like martensite and bainite as a major fraction. About 20% of polygonal ferrite is also there, and some 4 to 5% of retained austenite is there in the heat-treated conditions. So we just looked at what I'm just now showing is the post-tested microstructure at low strain amplitude, basically 0.4% after the failure is at 10,000 cycles approximately, and this is the large structures which is not deformed much, but this is the kind of a waviness it shows, that's all. But on the other hand, if you look at the retained austenite films, they undergo this kind of a deformation. They get into the small segments, and this also contributes to some extent to the maintaining the steady state. I'll come back to that point. And if you look at the other, I'm just going slowly from the lower strain amplitude to higher strain amplitude. Here again, it is a 0.5. Again, a lot of small segments of austenite is coming into the matrix. And the other interesting point to note here is, if you look at the polygonal ferrite, you see this is completely filled with dislocation. The contrast is quite clear, and then the kind of dislocation density which is there in this polygonal ferrite is quite high, and that's why you see this kind of a contrast. On the other hand, you can also see clearly that how this the lath structures are sharing and decomposing under the strain amplitudes. This kind of fatigue loading. This is 0.6% of strain, total strain amplitude. You can clearly witness all the deformation features here. Okay, so this is again another interesting features. Like I mentioned that all the retained austenite are getting into small segments, and what you see here in this particular micrograph here is you can see that some of the retained austenite is undergoing a rotation. Okay, the grain rotation also takes place, and you can clearly see this orientation of this particular grain is quite different from the remaining of the matrix. So some of this localized deformation of austenite colony is quite interesting, and we realized that all these small localized deformation mechanisms contributes to maintain the steady state in the material. This is what we have come to a conclusion later on. Okay, so I just talked about the stability of this multiphase microstructure. Okay, so what you are seeing here is this is at tested at 0 point after testing. I mean, after failure, you will see this. This is a microstructure. They're all quite intact. Some of the regions of this microstructure, it doesn't even look like it is undergone any testing. You can see this is. You can see that the laths are quite stable, and so it gives us an idea that what kind of microstructure will promote stability under fatigue loading. Suppose if you are able to produce throughout the matrix this kind of a microstructure, you are supposed to give, this material is supposed to behave like a super material under fatigue loading. Okay, so this is an idea you are getting. Okay, at the same time, if you look at all this, the interlath austenite, they are remaining quite stable, even up to 0.5% of, testing at 0.5% of total strain amplitude. So this again gives an idea. Okay, suppose if I keep this morphology, I can look at the process which can produce this kind of a morphology in a material that can remain stable under cyclic loading conditions. So this is the information you can get, fine prints information you get, which gives an idea to process the material in a particular way. Okay, so that is why the microstructure is quite interesting to look at it. And now I look at the other extreme conditions, like what are the softening mechanisms which governs this total failure. So what you are seeing here is the material tested at 0.8% of total strain amplitude. You can see that all the dislocations are enriched in the bayonetic lath, and then you also see some kind of a decomposition from the bayonet lath. It could be some of the localized decomposition of carbides and so on. And then what you are seeing here is, again, a bit complex to pinpoint what is happening exactly, but then most of the bayonetic laths are collapsing, and then it forms some dislocation cells wherever you have the ferritic regions are there. And then all the polygonal ferrites are filled with all the debris of bundles and broken laths and so on. So similar things are happening at different regions, and which these are all some of the primary softening mechanisms for this material. Okay, and this is another classical example where we have traced the shearing of the laths, how they are getting sheared under the fatigue loading, and then how the bayonetic region is looking like this. Okay, so there you are also seeing some closely spaced shear bands kind of features and the polygonal ferritic regions and so on. And the most important idea here is all these austenites which are stable up to 0.6% of the total strain amplitude, they start transforming to martensite. It's kind of transformation induced plasticity effect, trip effect, and which is clearly captured here. You can see that all the needle martensite forms here. And then another interesting point is it is happening just near the colony where you have the austenite has undergone some deformation, but only certain morphological, features of austenite are amenable to this kind of strain-induced transformation effect. So, which we could witness in other strain amplitude, higher strain amplitude. You can see that very nice martensitic features. So it's a kind of threshold strain amplitude. We could just say that beyond 0.6%, all the most of the austenite try to transform into martensite. That in fact creates further ground for softening, because the material is no longer able to absorb any strain because there is no scope, there is no free space available to accommodate any defects. So the further cycling on this heavily loaded defects only lead to a rearrangement of the defects that causes the cyclic softening. So we gave a kind of a schematic because though we show all the TEM images, but still it was a bit complex to somebody who is looking at it very first time. So we just considered only the bainite and martensitic kind of a feature, and then we gave this schematic how the deformation proceeds as the function of strain amplitude. So you have the austenite strips, interlock strips, they get segmented, which is coarse in the beginning, and they are getting finer and finer as the strain amplitude increases. And then all this bainitic glass getting some substructures development individually, and then also we can the austenite strips are getting further highly dense strips are appearing at as you go along the higher strain amplitude. And the very high strain amplitude, you can see that all the trip effect and carbide precipitation effect and so on and so forth is happening. So this kind of summarizes what happens in the total material. So we kind of gave a chart what's happening as the total strain amplitude and what happens to the number of cycles to failure and what are the connections between the microstructural features. So you can see that at higher strain amplitude, the softening activities are extensive sharing of bainite and martensitic glass and twin martensite. And you have the microstructural integrity, which are some of the microstructural features which are supporting the microstructural integrities are something like this. You have stable colonies of martensite and bainite, and deformation happens only in ferrite. Okay, and then you have the selective boundaries or colonies are only getting deformed, and then austenite forms kind of a fine segments. And these are the activities which is holding the microstructure together without softening. Almost, you can say that these are all, you have the hardening features and then softening features, and these are all the steady state microstructural features. So by doing this kind of a post-tested material analysis and conventional TM, we are able to throw little more of light to understand what happens during the fatigue loading and so on. So I'll just end my lectures, and then I know that I went through very fast, but in the given time, I thought I'll show something what we have studied in last few years. So if I'll be very happy to answer some questions if you have.
So thank you, Professor Shankaran, for this excellent lecture. If there are any questions, I would request the delegates to type it into the chat box. Okay, I think there is a question from Sandeep. He's asking how to distinguish between strain-induced precipitation and the usual secondary precipitation in a single-phase system.
Yeah. So the answer is quite straightforward here, because we observe the precipitation only at particular testing conditions. For example, whatever I have shown, for example, M23C6 at high temperatures, we could see only at particular tested conditions. But your question is how to distinguish this from the secondary hardening. So that is where so secondary hardening precipitation. So that is exactly, we just said that we have done some interrupted test. So where it starts and where it ends. So I showed one slide where you have the starting of the secondary cyclic hardening and middle of the secondary cyclic hardening and then final. So some kind of interrupted test will give you an idea where these precipitates are coming and what is already there in the heat treated one, we can able to nicely differentiate. Yes.
Okay. He's also asking, can we identify diffusion paths for elemental species in the matrix in case of DSA?
Okay, so well, see, this is very, I don't know whether I'm going to answer this correctly, but then you see, after the fatigue, the kind of defects which you create is quite enormous, right? So you are really giving a lot of channels for any elements to diffuse, right? Pipe diffusion and so on. The diffusion is going to be tremendously facilitated because of the defects, right? So when you say defect path, I mean diffusion path, I mean that is something like, you have everywhere, kind of all over the place you have the defects filled. So the diffusion is, in my opinion, it will be all over. Yeah.
He is also asking, what are the prominent signatures of occurrence of DSA observable in the microstructure using TEM?
Shankaran, if you click on chat, you will see all these. It may be quicker for you to.
Okay. Sorry. Now I'm seeing it. Yeah. Can we identify diffusion? But what some prominent features? What are some prominent signatures of occurrence of DSA? Okay, so some of the literature already reported, but we have not captured this. See, some of the typical signatures of the DSA observable in microstructure is the kind of short range ordering of, for example, iron nitride or some kind of very fine precipitates, which is there in the matrix. Okay, which we have only read in the literature, but in our system we have not studied because that time we didn't have the tool to look at it. But today we have a lot of sophisticated tools. We'll be able to capture those precipitates which are responsible for this DSA and so on. Okay, steps to be followed for replica technique in the case of fracture surface. Okay, I really don't know, but I have given the reference in the paper. I mean, my slides, they are all published results. So you will get this procedures in that paper, couple of papers I have given. What kind of facilities available to do micro hardness test to check the broken spring fractures? So you mean to say that, is it, I mean, I'm not understanding the question. Micro hardness test to check broken spring fractures. Okay. So if I'm not wrong, you can even do nano indentation. If that is you can do even today. You can even map the nano indentation. And of course, Vikram showed several examples in earlier talks. I mean, I don't know whether you heard him, but that's still possible. Yes. And what is interlath? Please elaborate. Okay. Sorry. Okay. When you have the microstructure of martensite or bainite, they form a lath structure. Lath is nothing but close to a grain, right? In a polycrystalline material, you have individual grains. So here it is a lath, means an individual grain kind of a thing. Grain kind of a feature, basically. You have lath boundaries, it's like a grain boundary, right? So bainite and martensite, depending upon the cooling rate of the processing, the microstructure evolves as a lath structure. So that is what lath I mean. Yeah. Okay, Professor Raghu, I'll stop here and we'll take the questions at the end. Yeah.
Yeah. Thank you, Professor Shankaran. I think we will give him a round of applause for his excellent talk. I think we are short of time. We have 2 more lectures. I think one is from Dr. Subir Kumar Bhaumik. He was a former scientist at the National Aerospace Laboratory, well known for his research in the failure analysis. And I now request him to deliver his talk, which I think relates to the failure analysis in the aircraft structures.
Good morning.
Please, yeah.
Are you able to hear?
Yes, yes.
Okay, I will just share my slide and then go ahead. No, I am not able to share. Is there any issue?
Bharti? There is an open share tray which is not great for you. After the, the microphone.
Yeah, I am clicking that, but it is not showing my screen. Huh?
Just give me a minute. I'll just contact
Sure.
Bharti if you can make him a presenter.
He's a presenter, that's what I can see.
Interesting.
Dr. Bhavik, is your share icon grayed? It is next to the leave button.
Next to the
Leave button on the top right.
Yeah.
So you click on that and then select the screen if you have 2 screens.
I don't know where is your icon. So if you find in one place the camera and then the mic, and maybe the next one is to the right of it is, yeah, I think you are getting it.
It is
Yes.
stop sharing, it is saying.
Yeah.
Great.
Huh?
Go to PowerPoint, you can.
You have to go to your window. Yeah,
Oh, there you go.
that's good.
Are you able to see it?
Yep.
Yes, but it's not in the slideshow mode. Yeah,
Now
it
it's fine. Perfect.
Good. Just advance a slide to see if we are able to see that. Laser pointer is there.
Mhm.
Can you move your slide once?
Yeah.
Yeah. Good. Now
Oh,
everybody
sorry,
is
took some time.
good. Thank you. Yeah. Please go
I
ahead.
think You have listened to two excellent lectures, one by Professor Bikram and one by Professor Shankaran. Professor Bikram has highlighted that fundamentals of scanning electron microscope and what are the different features you can study and how you can interpret the results. Professor Shankaran has shown that under low cycle fatigue condition, what are the microstructural degradation that you can see and how you can correlate with the behavior of the material at actual application scenario. In this talk, I am going to present some case histories, investigation that I had carried out when I was in CSR National Aerospace Laboratories. We do use quite a bit scanning electron microscopy for investigation. And actually, in early 60s, when the SEM was invented, it became a boon for failure analysts. As Vikram has already mentioned, that you can see the rough surfaces, you can do in situ analysis, and without any surface preparation, you can gather a lot of information. TEM we do not use so much, but nevertheless, in many studies, when a detailed information is required about the material, we do use TM, but very occasionally. Now, let me give a definition of the failure before I go ahead. It's a simple failure represents an adverse situation wherein a component or an assembly fails to perform its intended function satisfactorily. Very simple definition. And it doesn't mean that failure does not always mean that the component has fractured. If it doesn't perform properly, you can say it has failed. So in other words, you can say failure is an unacceptable gap between expected and actual performance. It also includes the human factor. So how do we minimize the gap? The engineers always try to minimize the gap. So it may not be possible to make the failure zero in this world. However small it is always, it will be there. But the engineering profession will try to minimize the gap. And how do we do that? To do that, we have no other option but to analyze the failure, find out what are the causes of the failure or probable causes of the failure, then take remedial measures. So there is a key role of failure analysis. If you see in the engineering profession, there are various criteria based on which you design a component or a system. I come from aerospace laboratories, and mainly we deal with aircraft related things where safety is the prime importance. So other things are also there, but safety is the prime importance. And based on that, you start designing, and then you manufacture, then you put into laboratory tests, certify it, and then put into operation. When an incidents and accidents happen, as I said, that you have no other option but to go for failure analysis. After the failure analysis, you give the feedback to designer to see that whether the design is all right and it has been done properly for the intended application. In some cases, in spite of the design is all right, the failure do take place because of various other reasons. In those cases, you come up with the regulations for quality control and quality assurance for which there was a lack in that, which might have resulted in the failure. So it is after the analysis, what we do is that implement certain recommendations from the lessons that we learned from the failure. If you see the engineering failure statistics, they are quite different in engineering, normal engineering components and aircraft components. You see here, the majority of the failure that takes place in an aircraft components is by fatigue mechanism. It's all of you are aware of that whether it is dynamic or static components, it undergoes vibration. There will be always cyclic load. There are other mechanisms like corrosion, but it is rarely you see that the corrosion, because of corrosion, loss of material is so huge that the cross section has reduced for overload fracture. Eventually, what happens, corrosion in most of the cases, they give rise to stress concentration and fatigue takes off. A similar kind of thing in case of stress corrosion cracking and hydrogen embrittlement as well. So if you add all those things, you will find that eventually about 80% of the aircraft structural failures that takes place by fatigue mechanism. So I will present some of the things which is fatigue fracture related in the future slides. Before I go ahead, as I mentioned earlier, that a detailed presentation has been made about the scanning electron microscopy, fracture, and other things. I'm not going into detail, but nevertheless, for identification of the failure from the fractographs, that's what I am going to show. Probably 2-3 slides will be appropriate to give you an idea how you are identifying it. So in wherever the failure takes place and the fracture is involved in the failure, you will have two kind of classification. One is static overload fracture that can be ductile and brittle, which can be classified as sudden failure. And another one is progressive fracture. And in this, you will have fatigue, stress torsion, cracking. These are a micro mechanism of failure, hydrogen embrittlement, stress rupture, etc. In case of progressive fracture, what you see is that it is different from the sudden failure, is that the crack initiation followed by progressive crack propagation that takes place over a period of time. And when the component is unable to take even the design load, it fails by overload. When you see the fracture surface in a macroscopic level, you may see that certain kind of marks on the fracture surface as the crack propagates, which is known as beach or clamshell marks. And schematically, you can see here, there is the initiation site. And it is exactly like what you see when you drop a stone in a water body. The ripples, that is from where the wave generates. Similarly, you can also extrapolate this and can identify from the crack initiated. And then you can go for further study. Since majority of the failure that takes place in aircraft industries by fatigue mechanisms, I am not going into detail of the fatigue mechanisms, but how to identify that it has failed by progressive fatigue mechanisms. Because as earlier I have shown that there can be different mechanisms which is characterized as progressive, and the macroscopic fracture features can be similar. But when you say by fatigue, you need to have some conclusive proof to say that it is indeed failed by mechanical fatigue. So I'm not going into detail into this, and as many of you must be knowing that there is how the fatigue crack propagates. It is basically at the crack tip. You can see a shear mechanism that creates the helps in propagating the crack in front, and they create certain kind of features on the fracture surface which is known as fatigue striations. And one of these marks, what you are seeing is that each striation is related to crack propagation in one cycle. But again, the features that you see on the fracture surface depends on what is the material plasticity you have and the crystal structure you have. For example, you have the top one, which is stainless steel. Very nicely, you can see the fatigue striations, and the bottom one is a martensitic steel. You may not be able to see it very clearly, but with a little bit of expertise and with the familiarity, you can always say that this is failed by fatigue mechanisms. So when you see such kind of features on the fracture surface, it is a foolproof signatures to say that the component has failed by fatigue mechanism. Schematically, if you see here, is a crack initiated at this location and it is propagating, and the curvature of the crack front that depends on the stress intensity factor that you have at the crack tip. Sometimes it changes the curvature, and that depends on the, as I said, the stress intensity. If you see that here, it has the fatigue crack has propagated up to this. After that, it has failed by overload fracture. So any fracture surface which has failed by fatigue, you will see two clear-cut regions. One is the fatigue fracture surface, another one is the overload fracture surface. The opposite side of the fatigue crack overload fracture surface, generally where the fatigue crack initiates. Now, how do we distinguish the overload fracture in metallic materials, ductile materials? In case of fatigue fracture, you generally do not see a gross deformation in the component because the crack initiates and everything takes place at the crack tip. But in case of overload fracture in ductile material, you will see there will be gross deformation. This is a tensile sample, you can see as simple like that. And the fracture initiates in the microstructural features, and you see the fracture surface something like this, which is called dimpled rupture, and there is mechanism for that. And you can probably see in some of the ASM handbook or fractography, you can find what is the reason why they generate such kind of dimples. So quickly, I'll go to some few case histories where the investigation, according to me, these are exciting investigations. Failures are unwanted, but when you do it, it is very exciting. The first one which I am going to present is that the accident that happened to an aircraft because of the turbine blade failure. The right side, what you are saying is typically how the turbine disc looks like. And these are the blades which are assembled onto the disc, and there can be different mechanism for assembling them. Generally, it is what is called fault tree mechanism, where the blades are assembled with the disc. So before I go ahead, those who are not familiar with the aero engine, you can see the different section of the engine. Cut section you can see here. We have a compressor section, which is generally called cold section. Then we have a combustion chamber, and then we have turbine. So, and the exhaust goes through that. The turbine is here generally made of nickel-based superalloy, and the different material that uses in the compressor section, right from aluminum to titanium to martensitic steel, depending on what is the kind of engine you have and what is the kind of thrust you want to generate. Now, coming to the investigation, this is like the background of the accident is that immediately after taking off, the engine flamed out, and the N1 RPM, that is a turbine RPM, it came down to 25 to 30% from 100%. And pilot tried to start the engine but failed. But when they found that the aircraft cannot be saved, the pilot ejected and the aircraft crashed onto the ground. Now, another background information is that when the preliminary investigation was done, it was found, it was almost identified that the one of the turbine blades that is fractured and caused the subsequent damage to the engine, leading to this flame out. Now, it is important to know that what is the history of this particular turbine blade. So the engine per se, it has logged in around 1200 hours, but the engine, it is overall is done after a stipulated time of service life. So in this particular case, the 74 hours before the accident, the overall was done. And during that time, all the low pressure and high pressure turbine blades were changed with the Cat A blades, that is a new blade. So eventually this blade, which is supposed to have around 1500 hours of service life, it failed within 74 hours of service life. Now this is where we use the scanning electron microscopy very effectively. So in any failure investigation, when the fracture is involved, it is very important to identify that what is the micro mechanism by which the component has failed. For example, whether it is fatigue or corrosion, stress corrosion cracking, and based on that, you progress further that what needs to be done to establish the primary cause of failure. If your identification of primary mechanism of failure is wrong, the whole investigation is wrong. So it is needless to mention that a lot of time is invested in identifying first that what is the mechanism of failure. So this is the fractures, part of the fracture surface of the turbine blade. If I go, this is this part, you can see here, there are macroscopically, it has two appearance. One has a granular and one has a slightly smooth kind of fracture surface. So if you have the experience, you will obviously say that, okay, this is likely to be a progressive failure. But by saying likely to be doesn't have any meaning. You will have to give the evidence, metallurgical evidences to say conclusively that it is failed by fatigue. So very simple. Now you can go to scanning electron microscope and examine this portion, and you can see that crack arrest marks and the fatigue striations, and you can clearly now identify that the crack has initiated, the blade has failed by progressive manner, and the crack propagation was by fatigue mechanism. But by simply saying that it has failed by fatigue, it doesn't solve the problem. Now the thing is, one has to establish that why fatigue crack is initiated in this particular blade. So the next thing is to do detailed fractographic study. I have given one slide here, even though you do a lot of analysis from this particular area. The magnified view is shown here, magnified view is shown here, and the magnified view is shown here. You can see that number of fatigue crack has initiated within the material, and they have propagated simultaneously over a period of time. Also, you can see some micro cracks have been generated within the material. Now, as we know, fatigue crack generally initiates from the surface, but it need not be outer surface. The material and the bulk of the material itself can have some surface, either from the manufacturing stage itself or during the service. It can create the surface, and from which the fatigue crack starts propagating, initiates and propagates. Now, it is very obvious that there was certain abnormalities in the material, within the material, which has resulted in this fatigue crack initiation and simultaneous propagation. Now the question is, what is the kind of defects that the material had that which prompted this fatigue crack initiation and propagation? Now the next thing is that you do a lot of in situ analysis, and sometimes you are successful in finding out something, sometime you may not be successful. The best way to do is that once you are very thorough with the fractographic analysis and you see that all the information you have gathered, then you can go for the destructive test to see what is there inside the material and specifically in the fatigue crack origin region. So now to summarize the fracture surface, as I mentioned a while ago, that number of fatigue crack they have initiated within the material and they are propagated. Okay, and this is how it is. It has propagated about 30 to 40% cross section of the blade, and then it has led to overload failure. Now the next thing is to find out that why this fatigue crack is initiated within the material. So you can have a longitudinal sectioning of the blade, what is available to you. The remaining portion is not available. It has gone into the engine and got distracted. And then you can do the microstructural analysis. What you see here is that magnified views are shown here progressively. You can see there is a stringer of material. Those who are familiar with superalloys, you know they have carbides. Basically, the carbides are necessary in the structure, but it has to be distributed. Okay, you should not have any stringer because the carbides are very brittle compared to the matrix material. And when the blade is strained, they may crack and generate cracks inside the material, which subsequently leads to fatigue crack propagation. So now the thing is that we see certain kind of abnormality here, and that there is stringer. Now, using the scanning electron microscopy on a polished metallography sample, you can identify exactly what are those phases. Now you can see here, I have given typical analysis of two particles. Number one, they have a different kind of morphology. You see the first one, which has a titanium peak, and you can see that it is a titanium carbide particle, the first one. The second one, if you see here, you have a lot of oxygen and aluminum, which is likely to be a slag in the material, which is entrapped during the melting and solidification process. You can do further analysis and you can find out the further confirmation, the elemental distribution in these phases. This is a backscattered electron microscope. You can see here. This is what you are seeing is that it is not a etched sample. Generally, when you do the composition analysis, it is advisable not to etch the sample, so you can get a better idea about the composition and the distribution of the material. But what you are seeing is the atomic number contrast. Now you can do the elemental mapping for different elements, that is what you have suspected. For example, if you do the titanium mapping, the bright spots, you can see there the signals from the titanium, and these are the titanium distribution. And you do for carbon mapping, carbon being the low atomic weight elements, it's not picked up very easily, but you can nevertheless see, and you can see the morphology, these are titanium carbide particles. Now you see the aluminum distribution, you can see that small particles, what you are seeing, these are aluminum, and they are also rich in oxygen. So you now confirm through this scanning electron microscopy, that is the fracture analysis and the composition analysis by proper technique, that there was indeed some abnormality in the microstructure, which led to the generation of crack inside the material during service, which then subsequently propagated over a period of time, leading to the failure. So the primary cause of failure in this case is inadequate quality control of raw material. Okay, so it is the raw material. Subsequent to this investigation, the certain norms are put down, certain sampling was done before the blade was fabricated to mitigate this problem. Now I go to the second investigation. This is an iron jack assembly of an undercarriage of an aircraft. You most of have seen that undercarriage, there is a retraction and extension mechanism, which is something like this. This is a piston, it goes inside, and you have the eye end here, which is with the thread, it is assembled here. Now here in an aircraft, where LSP means a limited series production aircraft, in a particular type of aircraft. During the ground run, they found that this component has failed. So the history is that landing since new is 326. Generally, the life of this component is more than 3,000 landings. The material that is used is this, and the hardness of the material is this. It is not only fracture in a particular component or in one component of an aircraft, but subsequent inspection showed the crack generation occurred in many such assemblies, and those were referred to the laboratory for investigation. So let us go ahead first with the one which had fractured into two pieces. Now, with the fractographic analysis, I am not showing a lot of fracture surfaces here, but you can see here that the component has failed by fatigue. You can identify from where the fatigue crack has initiated and which direction it has propagated. And you can see here the contrasting fractograph here, which is from the overload region, which is generally dimpled rupture. So you can clearly see what is how to distinguish between the fatigue fracture region is the overload fracture region. So here also it is, obviously it has failed by fatigue mechanism, okay? And the multiple fatigue crack has initiated all around the surface. So if you represent it schematically, that is how it looks like. So fatigue crack has initiated here. You can see here that the propagating crack front is concave in nature. If you refer to the ASM handbook, you will see a number of such schematic diagrams, and they will tell you what is the state of stress ahead of the crack tip. So generally, when there is a high nominal stress, generally the curvature of the crack front will be concave in nature. One more thing it is very important to note here is that the fatigue crack has not initiated at the natural mechanical notch which you have, key slot. It has started on the surface and it has started on both the sides. What it means is that the component has seen some reverse bending kind of load. So the fatigue crack initiated in either side, but it is asymmetric load. It is not symmetric load. If it is a symmetric bending load, so you will see the crack, the area of crack propagation on either side will be almost similar. So this is the fracture process. That's how the component has failed. Now you can come to another component which had not fractured, but it had a crack at the similar location. It is here. Now you can pull open the crack surface and you can do the similar kind of fractography study. And you can see again this is the freshly opened surface, which is very clear. And you can see little oxidized surface because it was exposed to the atmosphere while the crack is propagating. And you can clearly, with the macroscopic observation itself, you can find out that it is a progressive kind of failure. Now again, you map it. It gives you a lot of information that how the component has failed. The remaining 2-3 cracked end, they were also analyzed and the finding was exactly similar. Now, what are the probable reasons for failure? There can be a number of reasons: deficiencies in material of construction, deficiency in manufacturing, malfunctioning of the system, but no such things were reported, and during the analysis it was not considered. Service abuse, it is very difficult to believe because the failure has taken place in a large number of components. All right. Okay. Design related issues, assembly related issues. Now the thing is that one by one you can eliminate those. The material of construction you can examine against the standard, whatever has been given, and you find that there was no deficiency in the material of construction. But one more thing which came out, that is from the fractographic study, you can clearly identify that which location of the component in the assembled condition the fatigue crack has initiated. So you can see the reverse bending that is on the lateral plane, and from the designer it was learned that this is not meant for such kind of load in this particular case. So there was two questions which came, is that whether it was assembly related issues or underestimation of load. So subsequent to this analysis, the decision was taken, why don't we do the laboratory simulated test? And when the laboratory simulated test was done, you can see this is a tested sample, not actual failed sample. You can see the similar kind of failure. And surprisingly, you can see that the failed less than 1,000 cycles itself. And with further analysis, it was found that there was gross underestimation of load while designing the component. So it was a design deficiency. There was nothing wrong with the material or material selection. Subsequent to this, the design was modified and the component survived for many, many thousands of landing. Now coming to the third, may I know how much time I have? More? I have some time. So failure of collected booster rod of a helicopter. I think most of you have seen helicopter, but the control here comes from these three control rods, which is called lateral, collective, and longitudinal. And this is the input from the pilot, and that goes to the blades, like its orientation and the other things are changed based on the input that is given by the pilot. In the particular case, one collective booster rod, as shown here, it has fractured at this location. And when this fractures, that means that there is the aircraft, that is the helicopter, loses the control, and there is no way you can save the helicopter. And sometimes, if you are lucky, the pilots, they can crash land, and the aircraft may survive with very major damages and injuries to the pilot. But in this case, it was a serious accident, and this is the background of the things. The collective booster rod was in service for about 400 hours, and generally these components, they are designed that it is for huge amount of life. They are not supposed to fail during the whole life of the aircraft itself. But in this particular case, it has failed after 400 hours in service. Now again, as I mentioned earlier, the first thing you need to do is to identify that what is the fracture mechanism and where the crack has initiated. And you can see the fitting station. This is an aluminum alloy. You have a better signatures. You can map the entire fracture surface, and you can identify that what is the local crack propagation direction and from where the crack has initiated. So you find that the crack has initiated a number of cracks, multiple fatigue cracks initiated at the thread root, which is generally have stress concentration because of the mechanical geometry, and they have propagated to the outward direction. So schematically it is shown here. You can see the number of cracks it has initiated here, and they propagated outside, and when they have exited to the outer surface, you have two crack fronts on either side, and they propagate in the opposite direction. And as I mentioned earlier, that when the cross section is not sufficient enough to take the load, even the application load or design load, it fractures. Now the question is that why the fatigue crack is initiated. Now, to do that, you will have to have expose the surface carefully. So you can longitudinally section this component, and you can have these samples to examine the thread roots. So these are the thread roots you can see here. And surprisingly, you can see here is that in two sides, one side is of the thread depth about 0.97 millimeter, the other side about 0.36 millimeter. The design specification is thread depth is uniformly, it should be around 0.65 millimeter. So what it means is that while the thread cutting was not done properly. If it is done properly, it should be something like this. This is the other booster rod. You can check, section them, and you can check it. And this is as per the design and the manufacture. But in this particular case, you see there is a difference in the depth in the opposite, diametrically opposite direction, and that there is non-uniform depth. You can see progressively it is decreasing. You can also see here the engagement, thread engagement with the stud is one side is proper, the other side it is minimal. You can see here. Okay. So what it means is that if you do the proper thread cutting, it is internal thread cutting, you need a very precision machining. If it is done properly, you will have threads both the sides like this. If your tool is not aligned properly by, let's say, some degree, then one side you will have, this is supposed to have, you can see here, it's supposed to have truncated threads. You see in this case that it has pushed inside the material more, and inside it is less when the cutting tool is used. Okay, so there was a tilt in the tool while doing the machining, which resulted in this such kind of thread, internal threads on the tube. And when you, in application, what happens, the load that is transferred through the stud, that is the threaded component, it results in non-uniform stress distribution along the circumferential direction, along the thread roots. The one side it will be more, and one side there will be no load transfer. And because of the stress concentration you have already, the fatigue crack initiates. And once the fatigue crack initiates, it does not depend how much load you have on the component because of the vibration and other things, and it will fail by fatigue mechanism. And generally in such cases, you will see it will fail by high cycle fatigue mechanism because the load is not that great on the component to cause low cycle fatigue mechanism. So this is one example of the quality control during fabrication was not there, which resulted in the failure of this component, leading to the accident to a helicopter. Now coming to the main wheel hub of an aircraft, you have seen that wheel, you have a wheel hub. These are two parts. Okay, this is one part, another one part. And the accident is something like that. During landing, they found a part of the circumference of the your wheel hub. It had fractured and got dislodged, fractured, and leading to the busting of the tire. And there was slight damage to the aircraft, but not like the earlier ones. So you can see the component that is fractured here. So now you can cut this sample and take it out and can do the spectroscopy analysis. By looking at it itself, you can find out whether it is a progressive failure. In this case, it was a progressive failure. You can also identify that from where the fatigue crack has initiated. So now the full concentration is at this region where the fatigue crack is initiated to identify why the crack has initiated. Now it may not be possible in optical microscope, stereobinocular microscope. You have no option but to examine in a scanning electron microscope. When you put in the scanning electron microscope, you confirm that it has failed by fatigue. You are seeing clear fatigue striations here. But when you go to the crack origin region, you see there is a region which has a mechanically damaged. There was a nick at this location, and because of this stress concentration that you have, the fatigue crack has number of fatigue crack has initiated at this location, and then it has propagated, leading to the failure. So there was a mechanical nick, and most likely during the tire change, if you do not use the proper tool, that mechanical nick sometimes takes place, which is unable to detect. But all these aircrafts will have generally their periodic inspection is done. For example, in this case, the eddy current test was done in 2011 and the dye penetrant test was done in 2016 to check that whether any crack was present in the wheel hub at that particular time. After the DPT, when you do the dye penetrant test, because it has a protective layer, paint layer that is removed, then you do the DPT, that is the dye penetrant test, and again you put the paint so that it can be prevented from corrosion. But if you see your fracture surface, the fracture surface has a paint. You can see here, the magnified view is shown here. Now, what does it mean? That means that when the last painting was done, the crack was already present. So that when you applied the paint has seeped inside the crack. So in this particular case, there was lapse in doing the dye penetrant test. No one knows whether it was done properly, or there was deficiency in the understanding of the operator or the inspector who was doing this inspection. And since this crack was present there, then obviously it will fail by fatigue. All of you know during landing what is the kind of load it comes. So there are two things here. Number one is that the primary reason for failure is that you had a nick, mechanical nick, from which the fatigue crack has initiated. And to avoid failure, generally you have an inspection schedule to catch the crack if it is there in the component, developed in the component, but that inspection itself was again improper. So the thing is that number one, the primary cause, there was a nick, but there was an option for you during the inspection to reject this wheel hub, which was not done properly and led to this accident. Okay, and it was quite substantial. You can see the paint over 17.2 millimeter in length and 3.9 millimeter in depth. It can be easily found out even with the naked eye during the dye penetrant test that the component has one crack. Now coming to the last one, I think I have some time, another 5-10 minutes. Yeah. Investigation on fractured cross tube of a helicopter. This helicopter was being parked at night, and while it was being towing to the hangar, and suddenly there was a third sound, and this cross rod had fractured and they had tilted. Now, to have an idea, this is how the cross tube is, and this is the wheel. These are the two wheels, and this is connected with a cross tube. And the fracture has taken place exactly at this location. Okay, where a bearing was fitted. Now, this is the component. This is a starboard side. It has fractured at this location. The magnified view is shown here. This is the fracture surface. Now, clearly you can demarcate the two regions. One is the progressive crack propagation direction, and another one is the overload fracture. You can also see certain marks here, which is generally called ratchet marks. What it means is that on that there are multiple fatigue crack initiation, but they are not in the same plane. They propagated simultaneously inside the material, and after propagation to certain depth, they have joined together to form a single crack front, which then ran through the tube wall thickness, giving rise to two crack fronts in either side, and that goes. That is how you have seen in the earlier cases as well. So this clearly tells that there were, when you see the ratchet marks on the fracture surface, along with the beach marks or clamshell marks, you can safely conclude that it is not a single crack origin, there is multiple crack origin from which the cracks are propagated. Now this is a magnified view, you can see, and by tracing the crack arrest marks, you can find out that how the crack has propagated. You can see here, once it has gone through to the other side, as the crack is propagating in this direction, here you can clearly see the crack arrest marks. Okay, and generally you, in such components, because it is while landing, you have a heavy load, and generally you get very good crack arrest marks. The one, it's probably this between these two is crack propagation during taxi. Okay, so one crack, it is one landing, probably this is one landing. Sometimes you can count the number of landing. Okay, now the main focus is that why the fatigue crack is initiated. So this is the crack origin region. You can see here how the crack is propagating. Further, you can see, surprisingly, you can see this particular case, there are a number of spherical cavities, subsurface spherical cavities. I can see a number of them. And that is from where the fatigue crack is initiated. All right. Now we will investigate this further. So this is the summary which I have already told. Now the further confirmation, where the progressive crack zone is there, if you go to higher magnification, you see beautiful fatigue striations. To confirm, yes, it is a fatigue crack. And this is how you see in the overload fracture region, which is dimpled fracture. Now coming back to the crack origin region, you can magnify it and you can see there the fatigue crack is initiated at this location. Now what are these cavities and how they were formed? Now we magnify it further, you can see this is how it is. It looks like there was some gas entrapment inside the material. Generally you get like solidification voids, sometimes you see it. So now the question is, this particular component is made from the extruded tube, and the microstructure is broken so many times during hot working. How do you get such spherical kind of cavities inside the material? That is one suspicion you get, that how it is possible. Now all of them are subsurface. So you need further investigation. Then when you do it and magnify it, you can see here, those who are familiar with, you can see the dendritic structure on the surface itself. Now again, it confuses you. When the components is made from an extruded tube, how does this solidification structure you get on that? All right. So that is one thing you need to investigate. So you need to now go for the material study to see that what is the problem you have within the material. The general microstructure away from the fracture area, and you see that the microstructure is typical 2024 kind of thing, and there is no abnormality in that. But when you do the hardness survey, so that is where the fracture has taken place, you see the hardness is very low. And that It is very low. That means the microstructure is uniform and probably something has been done on the surface which resulted in such kind of hardness decrease. Now, what you can do is that now you can cut through the sample longitudinally to examine exactly at the fatigue crack origin region. Now you see a microstructure on the cross section which looks like a typical welded structure. You have a fusion zone, you have a heat affected zone, and this is the outer surface, and you can see the normal fractures of base material. And this is the fracture surface, and you can see the fracture has occurred wherever that cavities are there. There is another cavity on the surface. If you examine it in a scanning electron microscope, this optical microstructure, you can see that the fatigue crack has initiated from these locations. So now the thing is that it is established that something was done on the cross tube surface, and probably the material is deposited on the surface by some melting mechanism. What happens is that in such kind of component where the bearing is sitting there, over the usage, there will be wear and tear. So when the aircraft comes from overall, sometimes they do some repairing job. In this particular case, since there was a surface damage, they had deposited some material probably and then ground it to the surface finish and fixed the bearing there. Now during that material deposition process, which is a solidified structure, and certain kind of gas entrapment also had taken place. Now to prove that further, that this is the specification of the material, the tube should have this composition. So you can have the base material that has the same composition. The fusion zone, you can see the different material. You can see the hatch zone, there according to the base material. So this also proves, this is in situ chemical analysis you can do in the scanning electron microscope. It will not be exactly like a analysis which you do by spectroscoping method, but nevertheless it gives you very good idea. And generally we say that this is semi-quantitative composition analysis. All right, and depending on how you set the microscope, you can get very close composition what it should be. So the conclusion is that the failure in the cross tube was progressive in nature and occurred by fatigue mechanism, and fatigue crack had propagated in the tube encompassing about 30% of the circumferential length prior to giving way to final overload fracture at the time of incident. And it has been proved that there was some repairing job carried out during which an external material was deposited, and in that process some subsurface defects were generated, which was open surface like void, from where this, because this component is very heavily loaded, when you are landing heavy load comes, the cracks are generated from those voids, and obviously they are propagated by fatigue mechanisms and then led to the fracture. All right, so the recommendation was done later on. Now being in the laboratory, we do not have access to the logbook in the manufacturing agency what they do it, but it was found that the OEM, original equipment manufacturer, does not recommend any repairing of this kind. So the recommendation is obvious, since it is a primary component, primary load bearing component, structural component of an aircraft, a landing gear, and it was recommended that no such repair should be done, especially in the place where heavy load is coming. Now that is the end of my case histories presentation. Then the end notes, it is from the failure analysis point of view. So we always say learn through failures and design through failure analysis. As I mentioned in the beginning, unless you analyze the failure, you do not know what is the reason for the failure. You cannot take any corrective measures. I would also like to caution that a few engineers are knowledgeable in all of the possible interacting disciplines that are involved in given failure, especially in aviation industry. So it is only a team effort. Varieties of expertise is required, materials, engineering, many others. The team effort is often the only approach that can produce a complete understanding of the failure cases. So analysis of failure is indispensable for enhancing quality control and quality assurance. And last but not the least, if you are a failure analyst, ensure that history does not are learned from the past failures and preventive measures are undertaken. The last slide, I would like to acknowledge from whom I have learned this investigation a little bit. I had the opportunity to work with Dr. S. Raghuram. Then, of course, the agencies which have reposed faith in NIL for doing this investigation. And of course, first of all, the failure analysis group at CSIR. Thank you for your kind attention.
Thank you, Bobby, for a very nice lecture, doing multiple case studies and elucidating all the different modes of failure that have taken place and how they have been investigated. Are there any questions from the audience? If it is there, we can go through the chat box. Okay, there is one from Sandeep. Are you able to access the chat box, Dr. Baumik?
Yeah, I will access. Yeah. The turbines are designed to work for at least 40 to 50 years of service life. However, these materials are only tested for fatigue life of 10 to the power 7 and 10 to the power 9 cycles. Usually, why? Okay. So, number one is that no components in the engine is given service life by calendar years. Calendar life is not given. So, all engine components, they are given a service life in terms of service hours. Okay, so that is the first thing. So calendar life is generally given for the structure. For example, OEM, they will give 30 years and then you go for life extension. And in turbine, you have two components. One is the disc, one is the blade. The disc generally goes low cycle fatigue kind of loading because the mass you have and a complicated situation with the thermal gradient you have from high temperature in the hub and close to the blade, and then it goes down to towards the shaft to low temperature. Whereas the blade, it is high cycle fatigue kind of loading. All right. So I believe that a turbine would rotate well beyond 10 to the power 7 or cycles with a very high RPM. No, RPM is around 1300 to 1400 RPM. Generally, this turbine they occur, but it is not the RPM that is the mistake. Generally, people do it. All right. So the number of cycles and the RPM is entirely different. So the component that is seeing the fatigue cycle, number of fatigue cycles is much higher. So I do not know whether any classification is there 10 to the power 7 or 10 to the power 9 cycle. I am not aware of that, whether they are classified like that. Nevertheless, in practice, generally low cycle fatigue and high cycle fatigue, sometimes you classify based on the number of cycles they have survived. Considering any absence of material irregularity, is it possible that multiple cracks are generated in the vicinity of case of high cycle fatigue of a metallic specimen? Yeah, there is multiple fatigue. As I mentioned, all the cases, when you have multiple sites, it can initiate. Suppose you have a nick, it will have a dimension. From the area of the nick, everywhere the fatigue crack is initiated. But eventually what happens after propagating to certain depth, they join together and give a single crack front, as I showed in some of the investigations. How can I have access to some aircraft or turbine components or material from private entities, OEM, to perform some case studies on fatigue? This is a very excellent question. Unfortunately, if you are in a private organization, none of these national agencies will go to you. Okay, so these are confidential, and so generally they refer these failure cases to some national laboratories, unfortunately, in our country. Okay. So you most likely will not have access. However, if you want to do some study for some components, probably the OEMs they may give. Thanks to present detailed event, can you explain about hydrogen embrittlement and to help in failure analysis? Yes, as I mentioned earlier, that all progressive failures, you're likely to have some crack-arrest marks because they are propagating over a period of time. And as it is propagating, they're exposed to atmosphere for differential time. So you may get coloration. And also every loading cycle, the state of stress ahead of the crack may be different. They may not propagate in the same plane, resulting in some crack arrest marks. But in all those cases which I listed, like the fatigue failure, stress corrosion cracking, hydrogen embrittlement, you do see crack arrest marks. There is no other way but to do micro fracture analysis. In case of hydrogen embrittlement, you will get not striations. I have not shown that. You will get intergranular failure because it's a grain boundary phenomenon. As you know, the hydrogen that diffuses through the grain boundary, they recombine hydrogen atoms, creates positive pressure, and that leads to the separation of the grain. But stress corrosion cracking also you get intergranular failure. So there is a fine line to distinguish between this. One of the things is that you have SCM nowadays, you can do in situ analysis and see whether the corrosion products are present or not. And in case of stress corrosion cracking, it is completely intergranular, like rock candy structure you will see. In case of hydrogen embrittlement, you will find limited ductility at the grain boundary. So on the facets also you will see a very shallow dimples. All right. The another thing is that stress corrosion cracking always starts from the surface. Hydrogen embrittlement, it starts from subsurface. So the crack origin region you have to examine very carefully. Sometimes you may be successful, sometimes you may not be successful. But with little bit of success, a little bit of practice, you can easily identify whether the component has failed by hydrogen embrittlement or stress corrosion cracking. I hope I have answered the question that you asked. Anything else?
I think there are two more questions. One asking about complex stress states and the design
As the
criteria.
turbine blades are subject to complex stress states, so on what criteria? TC fatigue, TT fatigue, etc. The material process for the design. Yes, I think you can ask this question to the next speaker, Dr. Sundar. He will properly answer. I am a metallurgist, practicing failure analysis, but not a designer actually. So I'm sorry. You can ask the next question to Dr. Sundar. I'm sure he is the proper person to answer this. Please throw some light on how to obtain cross-sectional corrosion morphologies through ACM, which is due to fatigue, roll-up polishing, or sectional cut. Yeah, light on cross-sectional corrosion morphologies. Okay, you'll have to prepare the cross-section of the sample. If it is a stress corrosion cracking, it generally penetrates inside. So you will see some amount of pits on the surface, and generally crack initiates from the bottom of the pit and it propagates around the grain boundary. So wherever the stress corrosion cracking is there, if you make a cross section metallographically prepared, you can clearly see, even in optical, you can see that there is a grain boundary oxidation, and then you can put in the SEM in situ analysis. You can do and find out what is the corrosion agent that is responsible for the. In case of pits, you will also see the pits. So you'll have to prepare the sample. Sometimes it is, if the pits are very small, then it's very difficult to cross section it. But since you will have number of pits, so you slowly keep on grinding and polishing and keep on seeing in the metallographic sample. So it is a little laborious process. So little bit of material you will have to remove, and then you will have to have examine in the microscope, go back if you don't see it, and again I do it. It is little laborious process, but you can do it very easily. It doesn't take much time. I hope I
Next question, probably we will take that question and move on to the next speaker. Correlation between stress corrosion cracking and crack branching.
Oh, yes. There is a distinct difference between, though the question is different, I'll answer that. Stress corrosion cracking and hydrogen embrittlement, what I was telling is that stress corrosion cracking, you will have extensive crack branching. As I said, that if you make the cross section, you will see a pit on the surface, but inside you will see the crack almost like a tree root. So much damage will be there. In case of hydrogen embrittlement, you do not see crack branching. That is one of the identification for stress corrosion cracking. Anything else?
Oh, no, I think I will have to do a time management. So
Thank you.
yeah, we will thank Dr. Baumik for giving a very nice lecture. And, it's basically taking you through the real life problems and how they have been handled. And in fact, I have some interesting question to ask, but I will not do it at this point of time. I'll do it privately with him because of want of time. So thank you very much, Dr. Baumik, for his excellent presentation. Next, we move on to the last talk of this. Well, it is not the morning, but I think it's almost post lunch or the lunch afternoon. So this is by Dr. Sundar, who has had, as what I introduced in the beginning, more than 40 to 50 years of work experience in understanding the failures and the failure mechanics through the electron microscopy. His classical works are being referred to in many literature. So without much of an ado, I'll now request Dr. Sundar to start his talk.
Thank you. Thank you, Raghu. And I must say that it's nice to be the last to speak because a lot has been covered by the three previous lectures, which actually covered pretty much of what you would require to appreciate the content of this lecture. So I'm, in a much better position as a researcher than the previous speaker, Dr. Baumik, because when you do failure analysis, you're doing the work of a detective. It's a whodunit job when you're looking at something and trying to figure out what caused it. I'm going to now talk about the opposite, where you know exactly what caused the failure and you try to learn about how a fatigue crack grows. And that's an important exercise too. I will start with an introduction on why this kind of work is required, and then proceed to describe some case studies. Practically all of what I'm going to describe is work that I was involved with, or I have taken the initiative to do, so I should be able to address questions without much of a problem on any of the slides that you see. Now, there is a bright side to everything, and even though fatigue is a big problem, fatigue cracks actually are the bright side of fatigue because they serve as visible indicators of condition. Dr. Baumik showed the picture of a wheel hub where a glaring defect was left undetected, and it led to a catastrophic failure. But that's not what it should be, because inspection periods, they are a very vital part in any structure that's maintained on condition. And today, all aircraft structures and engines, aero engines, they are operated on condition. Practically, you don't give a life to them. What you say is, at the next inspection, do you see a defect? If you don't see it, you can proceed to use it till the next inspection period. And that's the beauty of it, because that is how, aircraft, many of them that fly today, you may not believe it, but they actually do more kilometers on the ground than many of the cars that we drive. So they are very, very heavily used, even though they are the most highly stressed structures that you'll find in engineering practice. So that is the bright side of fatigue cracks. And that is that if you are able to predict how long it will take for a crack to grow from a detectable size to failure, you've got it made, because you can safely use the structure quite indefinitely. And this is very important because if you look at fatigue life, there's a very huge scatter in fatigue life, large scatter in fatigue life. But in fatigue crack growth, the scatter is, an order of magnitude less than in fatigue life. Therefore, if you go by fatigue life, if you go like Dr. Baumik mentioned, one of the OEMs said, this this particular component is not subject to inspection or repair. You just have to chuck it. Then it becomes very expensive. Whereas if it is something that you can inspect and then continue to use, the investment is really worthwhile, and you're not compromising on safety. Whereas if you go by fatigue life, you are in a way compromising on safety, because there is, after all, a probability that the part will fail before the rated fatigue life because of the large scattering. So that is why I was very lucky to get involved with fatigue crack growth studies. And I believe that I learned a lot in the process, and I would like to share with you today how much electron microscopy can help you in understanding fatigue crack growth, because a test system in the lab, it's different from structures and machines that are on the road. Because a test system is in the lab, and it's not going to cost you a whole lot to reproduce fatigue failures that are likely to happen in service. And when you combine that with a scanning electron microscope, you have a formidable tool to understand how real cracks will grow. Now, the sad part and an important part is real cracks grow under conditions like this. This is for on a fighter aircraft. These are the kind of loads that fighter aircraft will see in its life from flight to flight. Passenger aircraft see gust loads. Engines, discs see loads like this. Helicopters see loads like that. And the idea is, I get the crack growth rate versus delta K curve from the lab. How can I use this curve to predict how a crack will grow under these conditions? It's really a challenge, because the crack isn't going to grow under these conditions in the way in which you thought it will grow. When you use a lab coupon, use ASTM standard E647 and generate the data to get this curve. So you have to gain an understanding of how a fatigue crack will grow under complex load history. You have to look at the mechanics of it. You have to look at the mechanisms involved in each material that you're dealing with. Then you have to develop an analytical model to compute how crack growth will occur in service. And then, of course, you have to track the loading conditions from flight data recorders, combine it with inspection, and ensure that you have a long service life. And the huge advantage that fatigue crack growth gives, and particularly when you have a microscope to look at how the crack grows, was discovered pretty early. And here are pictures from the early 60s. These were obtained on an aluminum alloy by Macmillan and Pellew at Boeing, and then they appeared in a classic ASTM special technical publication in the mid-60s on how a crack grows under program loading. So they applied load sequences of different kinds, including this one, for example, here. And you can see that there are 3-4 cycles in between, which are slightly shifted up, but of the same amplitude. But you can see that the very first one sees a huge jump in crack growth, and that's followed by a much slower crack extension. But the important thing that was obvious at that time was that the crack extension practically proceeds at the microscopic scale with digital precision. You not only find that the cycles match the number of striations that you see here, but even the spacing is so highly reproducible. But and the other advantage is that because of this nature of crack growth, particularly in aluminum alloys, you can use it to learn what's happening. And you can then do a more complex load sequence that Macmillan and Pellew use, and they were able to tie up what happens under this complicated load sequence. You see, they found out that exactly that much of crack growth is associated with this many cycles. And they figured that out because they kept repeating this sequence in exactly the same ways over here. This sequence was repeated. Now, the sad part is, even though most of us believe that striations indicate fatigue, the unfortunate part is that striations form over a very narrow interval of crack growth rate. Practically, 1.5 orders of magnitude, somewhere little under 10 to the power minus 4 millimeters per cycle up to little over 10 to the power minus 3. That's a sad part. But most of the fatigue life is consumed in this part, 10 to the power minus 7 to 10 to the power minus 5. And that's where, unfortunately, you don't see striations. So if you look at the DADN curve, you can, in aluminum alloys, clearly, you have a region, narrow region where you have striations. Above that, you have the quasi-static component. And in aluminum alloys, that is given, and Dr. Baumik showed some of those pictures as well. You have the voids, large voids that you see here. They are associated with the rupture of secondary particulates in the alloy. And then you have the microvoids. I'll come back to this a little later. But at much lower growth rates, the fracture surface is practically featureless, faceted in some materials, but you have river patterns like this. And I've even seen research papers where the authors have confused these river patterns with striation patterns. You see, the river patterns are parallel to the direction of crack growth. The striations, they are normal to the direction of crack growth. And to show that is the case, I have put these marker loads over here. You can see the crack front marked by periodic markers. And most of what I'm going to discuss with you is going to relate to these markers. Because when you put these markers, you can actually figure out exactly what was the crack front at that time. What that means is that if you're planning experiments involving understanding how a crack grows, you have to be ingenious in designing the experiment so that when you go to the microscope, you can actually understand how the crack was growing. So imagine if I were not to use these markers, I wouldn't know what was the rate of the crack growth. I wouldn't know the direction of crack growth because I'd be confused by the dominant features over here, that of river patterns. Now, let's look at some examples of what we've learned about the fatigue crack growth process over the years using engineered loads. This is some pretty early work in the early 80s. Dr. Dash and I did these experiments at the National Aerospace Lab, where, in the early 80s, there was a lot of discussion about crack closure. And ASTM has a standard testing practice to measure crack closure. So this is how you process load versus crack opening displacement data to see where the deviation is from elastic compliance response. And then you say that that's where the crack closure load occurred. It's important to know the crack closure load because it's only the load cycle over which the crack is open that contributes to crack growth. So it's a very important parameter. If you consider that crack growth rate is a power function of this range. So it's very important to know exactly where the crack opened. And it seemed kind of funny that even a standard practice gives you this margin, huge margin of variation in crack closure load. And that has been a subject of controversy. You find a lot of people in the community who say all this crack closure is, it's nonsense, and others swear by it. So we did this simple experiment where we applied a block of load like this. At that time, we had to work on a transmission electron microscope of probably Jurassic vintage. So we had to coat the replica, and I learned a lot about patience when I tried to coat the replica and then cut it and then float that little coating, put it on the transmission electron microscope after fishing it out with a foil grid. And we found indeed there are equally spaced striations. You can actually count the number of equally spaced striations. And from that, you can precisely say what is the crack opening load. And we found that, at the edge of the specimen surface, you have a higher crack opening load. In the middle, you have a much lower crack opening load. You can see there are hardly any equally spaced striations over here. this was a very interesting piece of work because it showed that crack opening load varies significantly. It also showed that with the microscope, you can determine it precisely. But unfortunately, it also showed that crack opening load is a very difficult parameter to measure unless you're doing your PhD or something like that. And then considering, and having this enormous faith in the digital reproducibility of striations, I came up with this idea. Why not punch numbers onto the fracture surface? So we came up with what you can call as a binary coded load sequence, where the number of the applied load block is punched along with the crack closure sequence. So this part of the sequence is used to measure the crack opening load. And then this binary coded sequence punches the block number. So why is this important? Because then I can go to the fracture surface and say that, this was the crack closure load in this particular applied block. So we tested a specimen with a notch, allowed a crack to form naturally, and then we were able to map the crack closure load. So you can see here, this is the notch root, that very close to the notch root to the very high closure load, 45%. And as we move into the middle, it came down to 28-30%. This was a pretty decent work, but I would say that if you want to do it, you also need to know how to generate these loads. And unfortunately, most of the commercial available testing machines, they don't allow you to do that. You have to design these loads and punch them off. There are a few exceptions to this digital reproducibility of striations. And I just want to show you one example. This is, of course, much later on a good scanning electron microscope. When a crack branches, I applied 10 cycles. When a crack branches, I get to see striations on both the cracks, basically on the branched crack as well as the original crack. And in the literature, I was amused to find rather that somebody noted that, he counted more striations than the number of load cycles he applied in a block. But that's probably because he was looking at a branched crack. Because here you can see more than 10 striations. So you have to be careful about how you use the microscope. And as Professor Vikram showed initially, you have very tremendous depth of focus on a scanning electron microscope. But here you can see, if you edit this picture using Photoshop, you can see exactly how it was before the branch opened up. This is an edited image. Now, another interesting application of microscopy to confirm certain things that we are given to accept is the rainflow cycle counting. And now rainflow cycle counting is a very important part of fatigue analysis. Supposing you have a random load sequence like this, you can do rainflow cycle counting and reduce that to a table of load cycles, different range of load cycles and how often they occur, so that you can use that in analysis. But the question is, does it apply to fatigue crack growth? Well, we actually in the 80s did an experiment in NAM to figure out on a sequence like this, where you see here, this complex sequence actually consists of multiple cycles embedded in a large cycle. So there's one big cycle and several small cycles. And like that, these are just the large cycles for reference, and these are just the small cycles for reference. Again, on the microscope, we were able to get a segment digitized, and from that digitized sequence, we confirmed that rainflow cycle counting is applicable to fatigue crack growth. Now, that was a pretty fundamental piece of work, but it's an important piece of work if you're in engineering and you're using something which is used for fatigue analysis, at the notch for cumulative fatigue analysis, we were able to show that it actually works in fracture mechanics as well. Now I'll come to several case studies of applications of microscopic markers. And I think I would make an arrogant claim that we've done much more work on this than anybody else in the world. So to start with, here is a load sequence that we used in experiments at the Air Force labs in the US, where we used 3 segments, each you see of 2000 cycles. These are small amplitude, so you won't see striations from these cycles, right? You won't even see striations from these cycles because there are 10 of them, and on the picture you can only see 1 line because the growth rates are very small. We were very interested in what happens in the early stages of fatigue. And if you apply the crack closure concept, the crack would be expected to close somewhere at this level. So we selected higher stress ratios just to ensure that there was no crack closure. And if you go by crack closure theory, you should get equal crack growth rate in all these 3 segments, this one, and this one. And we were kind of surprised to find that's not the case. See, in this one case, it's a large crack extension. Crack is growing from right to left. And in the third step, it's a very small crack extension. So this was very intriguing for us. And we got to work on to figure out what exactly was happening. And we actually found that it led to a discovery of apparently the opposite of what was expected from crack closure based interpretation of fatigue crack growth. That is that, in the case of a long crack, you see here, there's a long crack on this specimen. In this case, the spacings are equal. So this supports the crack closure theory. But in the case of a notch root, this is a blunt notch actually, not much of a stress concentration, less than 1.5. We found extreme difference. You can see, if you see carefully, you can see in the first step, there's substantial crack extension. In the last step, there's hardly any crack extension. So going by crack closure, I should draw the conclusion that I have more crack closure over here than over here. But that runs against any analysis, because any analyst will tell you if it's a short crack, it's likely to see less closure than a long crack, because the long crack has a large wake and the loads are higher. So we were kind of taken aback, and we actually wrote up a paper about the so-called short cracking effect and forgot about it until I went back to the Air Force lab and looked at this kind of phenomenon on the fracture surface. These are secondary particulates. There's a very rare picture of a secondary particulate still sitting on the fracture surface because these are microvoids. So this is a picture I took from another slide, previous slide that I've shown you, where you can see the microvoids and the large voids from the failure of these particulates. And you can see that there's a dimensional difference. These are, about 5 microns in size. Microvoids are much less than a micron in size, fraction of a micron. So you shouldn't confuse one with the other. I say this because I find several papers in the literature where they look at voids from secondary particulates and call them as microvoid fracture. That's not right. So and then was just examining these voids left on a fatigue surface under very low growth rates. And it seemed apparent that here is the notch root. The crack took off from here. It was very clear that a crack had already formed internally. And this large crack was intersecting that particulate, but at a different height which is why you have this wall and a wave forming after that. And this is not because of any special reason other than I just remembered the day that I took this picture. I was shocked to find that within this cavity, there were the marks left behind by these 3 steps, by the markers. You can see these. And I initially thought that, they were artifacts, because up till that moment, the common belief was that these particulates don't separate by fatigue, that they are broken statically or they just fall off. But this picture showed that there was an interfacial crack separating the particulate from the matrix. So I ran up to my colleague, John Porter, who he's like a magician. He put the other fracture surface onto the microscope and found the same location on both the fracture surfaces. And he said, Sundar, this is not an artifact. You really hit upon a real void with the marks in it. So it turns out that in the secondary particulate, the crack was growing. And this is a picture where, they see these marks much better. These are very, very low growth rates. And these are very, very small cracks, right? This one is hardly 100 or 200 nanometers. So this is probably the smallest crack you've seen anytime. And yet they were following, first of all, fracture mechanics principles. They're equally spaced. And that was an intriguing thing, because you remember on the short crack that I showed you earlier, the spacing was not equal when the crack was small and when the growth rate was small. So the question arose, why is it that these are equal and those were not? You can also see that the cracks form on all sides of the particulate. That is because this process is happening ahead of the main crack tip. And because it's happening ahead of the main crack tip, and there's a lot of physical constraint, these areas are actually seeing hydrostatic stresses. That is, I'm cycling uniaxially, but the particulate is seeing stresses from all 3 directions. And that is why you have these interfacial cracks growing on all sides. And the reproducibility is superb, thanks to the markers. And this is again, I'm going to say this time and again, you're wasting your time if you're doing experiments in constant amplitude fatigue. You got to use more complicated load sequences, which are easy to generate on computer-controlled testing machines. And you can see the equal spacings, with tremendous precision. Compare these with the short crack growing out of the notch. Here, they are grossly unequal. So obviously, this had nothing to do with crack closure. Could it be that this crack was growing in high vacuum and that was growing in air? And that was the difference, that we perhaps have discovered what causes the mean stress effect in metal fatigue. And that was unknown for 160 years. It was a mystery. So I was able to convince the management of the Air Force lab to give us a high vacuum machine. And on that high vacuum machine, we actually did this test using the same sequence, except that we would apply a couple of blocks in air, I think 5 blocks in air, and then we would switch to vacuum. Apply 5 blocks in vacuum, but in vacuum, we would apply more cycles. In the 3 steps, instead of 2000, we would apply some 5000 cycles. This was a long test because it was a naturally forming crack. And this test took about, I think, 4 or 5 weeks, because we would have to wait for 2 days for high vacuum to develop. My colleague over there, who is familiar with vacuum behavior, he said, if you want to eliminate the effect of air of the moisture in air, of the hydrogen that's released when metal oxide forms, you have to go to very high level of vacuum. So we waited for till it hit the 10⁻⁸. And lo and behold, you can see in air the difference in the 3 steps: large growth, reduced, and further reduced in these 3 steps. In vacuum, they are perfectly equal. And this shift is immediate. So this effect has nothing to do with crack closure. We confirmed that it has to do everything with the environment. So now, we got kind of an understanding of what causes the residual stress effect in fatigue, what causes the mean stress effect in fatigue, which was not unknown. Which was not known for all these years that fatigue has been. But then, because the Air Force lab works on engine materials mainly, they asked me to show the same effect in Inconel iron 100. It's an Inconel nickel-based superalloy at 650 degrees. And marking that material at high temperature was a challenge. It was a huge challenge because it was very difficult to mark. But after some iterations, I figured out that if you apply a lot of small cycles, that actually leaves a mark. So using just 2 steps, just to keep it simple, when we did the test, we got more than a 10-to-1 retardation in crack growth in the smallest step. That is, the effect at high temperature is much more than in at room temperature in aluminum alloys, which means that it again confirms the significance of the deadly combination of environment and local stress. In high vacuum, you see the crack extension is identical. So I believe that this was probably the best example one can cite of how you can design fatigue experiments and then go to the microscope and understand the process much better. Here is another experiment with a hold time. See, here's the hold time. And you can see that the crack has grown in fatigue over here. In fact, the 2 steps that are shown here, you can see the difference in crack extension. Because the crack growth rate is higher over here, the difference between them is less. That is because this phenomenon of the mean stress effect and residual stress effect, that is seen at threshold. As you go into the Paris regime, as the crack growth rate increases, as the fatigue life comes down, the effect of residual stress and mean stress, they also come down because of the increased contribution of reversed inelastic strain. That is why nobody talks about the mean stress effect in low cycle fatigue. It's a high cycle fatigue phenomenon. Similarly, in crack growth, both stress ratio and load history effects, they become dominant in the threshold region. But then remember, that's what controls fatigue life. So it's a very important point to remember and to take into account while modeling the process. And you can see when you come back here, the whole time switches the mechanism in crack growth. So from transgranular fatigue crack growth, you have marked the crack front, and that crack front jumps ahead in the mid thickness area because here you have planes strain conditions. You have hydrostatic stresses, and Dr. Baumig mentioned how the crack branching occurs. You can see here that the grains are practically being separated from each other as the crack branches off in different directions ahead of the crack tip. And it does so more in the mid thickness region than it does at the specimen surface, where you have plane stress conditions, and therefore you have less environmental attack. This is a magnified picture where you can see the huge difference between how a fatigue crack grows at high temperature and how crack and hold time. Here's an even more magnified picture to look at those voids where I showed you those concentric crack growth, and to look at these grain surfaces, basically individual grain surfaces, you have to go down to very small working distances, so about 5 millimeters. Now, what happens in vacuum when I have fold? I don't have the environment. Therefore, I don't have stress corrosion cracking. Instead, I have crack tip blunting. So, and this is a reconstructed picture using Photoshop, where you can see the crack was at this point switched to from cycling to hold. And during that hold time, I think it was just about 100 seconds, the crack tip blunted. So creep phenomena come in. I don't have any oxidation because it's high vacuum. And the crack tip just blunts. And then when I continue cycling, the crack starts growing in fatigue from the top as well as the bottom. So I have two cracks. So you see the crack started growing inside over there and over there again. We were able to, basically you can edit this picture and get the situation the way it was before the dwell was applied. So it's so different from what happens in air. In air, you have stress corrosion cracking. Now, with all this knowledge, it was possible to put this new understanding to the test of different types of load sequences. And I want to just cite a couple of examples for you. This is an example of near threshold fatigue crack growth. You see blocks of 25,000 cycles were applied, identical blocks, very small amplitude. These cycles are applied on the rising half of a large cycle. And these same cycles are applied on the falling half of a large cycle. And the sequence is repeated. And also at the maximum. So identical amplitudes, one on the rising half, one on the falling half. And you can see what happens. That is the crack extension on the rising half. That much of crack growth from here to here. I apologize. This is at the maximum. And this little bit of crack extension, which is actually sub-threshold on the falling half, and on the rising half is this one. I'm sorry, I confused the two. And here the crack has gone through a secondary particulate. You can see that particulate sitting there. You can see the river patterns. Imagine if I were not to use markers, I would never have figured out how the crack was growing. So it turns out here I have elastic unloading that is shown schematically over here. I have elastic unloading, which takes the local mean stress way below what it would be on the rising half and a little less than what it would be at maximum. And that is what protects the crack tip from environmental action, from cycle by cycle environmental action, so to speak. So it follows from this picture that near tip residual stress controls delta K threshold. This is not about crack closure. Crack closure is a different phenomenon. These are all experiments you can see where the cycling is at a sufficiently high mean stress to avoid crack closure, to avoid the confusion which would be created by crack closure. Because crack closure is something you can accommodate analytically and do so quite well. There's a lot of very good modeling work in that. So I can add this to that and get the right values of threshold. So here at a higher growth rate, you see instead of 25,000 cycles, just 2,500 cycles of larger amplitude, you can see the effect is not so dramatic. This is the crack extension on the rising half. That is a crack extension on the falling half. And if you go into the Paris regime where striations form, there'll be no difference between these two. And we have results of that kind too. So here is finally an experiment that I'd like to describe, which essentially shows how you can take this to a more complicated load sequence. So to do that, we took the transport aircraft load spectrum, which has hundreds of thousands of cycles, did a rainflow cycle count on that, which I showed you was valid, you can do it, and took the smallest amplitudes, that is steps 0, 1, and 2, and put them either on the falling half, like over here, or on the rising half. So we call this as low-high. We call this as high-low. And then we model the stress ahead of the crack tip. And we can see that in step 0, in high-low, my local stress, near tip stress is pretty low, negative. Whereas in the low-high, it's positive, which means I'll have a lower delta K threshold, for this stress, and a higher delta K threshold for this stress. And this relationship was obtained using a new test method, which we developed. And today, I'm happy to say that we have a process going on in India involving 10 labs, which is looking at reproducibility of this relationship and the method to deliver this relationship. And we are likely to adopt it as a new standard testing practice. So you can see what comes out of microscopy, a totally new testing practice, which has a tremendous scope in engineering application. So we were able to model these numbers, and then we tested 2 specimens, one under the high-low spectrum, the other in the low-high spectrum. And here is a fractograph at the top. By the way, these are computed DADN curves for the low-high and high-low sequences, accounting for the effect of near-tip residual stress on threshold. So the red line is the low-high, the blue line is the high-low. And the difference in growth rate at this particular stress intensity value is a factor of 5. And here is a picture corresponding to the same growth rates. And you can see how much the crack has grown in step 0 in low-high, and how much it has grown in high-low. It has practically grown very little. So it's about a factor, 20 to 1 difference. And if you look at the other steps, you have the same situation. You have similar growth rates in the striation mode. You see in step 3, where you already have the Paris regime striation mode, the growth rate is the same, 6.31 10 to the power minus 4. Here it's 6.4 10 to the power minus 4. So from these 2 pictures, we can say that thanks to the work done on the electron microscope on fracture surfaces obtained under highly controlled and specially designed experiments, we can develop a much better understanding of what's happening in a way that's useful for engineering practice. And that is shown by these computed values of delta K threshold as a function of crack size. Here I have superposed scaled pictures. How are they scaled? I took the crack extension in step 3 and matched it with the step 3 in the low-high sequence. But this is from the high-low sequence. And you can see the crack extension in the entire block is about 1/5 of what it is the low-high. So this gives you a clear idea that we finally are able to describe the fatigue crack growth process for engineering applications like aircraft load spectrum or other load spectrum with microscopic consistency. So what I mean by microscopic consistency is we are not only getting the right result, but we're able to show that we are getting it because we got the right result for each of these different load steps that you see. So what is the kind of summary I'd like to make based on whatever I've described to you? and that is that a fatigue fracture surface created by specially designed load sequence has a lot more to offer than one created by what, unfortunately, most scholars seem to prefer to use, constant amplitude loading. The basic science of fatigue differs little between metals. If at all possible, one should choose a fractography-friendly material. And I would always recommend aerospace-grade aluminum alloys because practically you can write on them, as I showed you with the picture on binary coded loads. First, remember the power equation between crack growth rate and applied delta K. It helps you select the right magnitude of applied loads in testing. Marker load should be selected to do just that. They should only mark the crack front. They should not contribute much to the crack growth process, and they should not distort the fatigue crack growth process. That is, they should not distort those conditions that you want to study. And as I showed you in the case of the nickel-based superalloy tested at high temperature, low amplitude, low stress ratio cycles will help you mark without affecting the process at all. Sequences, they repeat with digital precision. So you should always apply repeat sequences so that you can confirm that what you saw in one picture is not different from what you see in another picture. It's also important to remember that you have to select the duration of your load sequence, your repeatable load sequence, such that the crack extension from the entire sequence will fit into a single grain. Because once the crack path crosses the grain, you're going to have a distortion. And you don't want that. You want to get pictures which don't confuse you. Now, striation and marker band size, they correctly reflect the relative contribution of segments in your load sequence. However, they may not accurately represent the macroscopic growth rate because of other mechanisms that might be present, which you have not seen, because you're only looking for what you want to see and you've missed out something. And there's also the question of the tilt or the fracture surface. Vikram covered it in the first lecture. So your scale overall might be different, but because whatever you're seeing from different parts of your load sequence are on one picture, and you're only looking at the relative contribution, you cannot go wrong. Of course, the best part is when you're doing work like this, you don't need large test specimens, because you're going to a microscope after all. So even 0.5 millimeter, 1 millimeter of crack extension are enough to write a paper. Thank you very much. If you have any questions, I'll be happy to address them.
Okay. Thank you, Dr. Sundar, for this exciting lecture. If there are any questions from the audience, you can type it in the chat box. There is a compliment from Deepa Srinivasan saying beautiful microscopy.
Oh, thank you, Deepa. You're always very kind.
Well, I think I don't see anybody who has typed in either. Oh, okay, there is Mayank who is asking, can we apply these theories for composite materials?
No, you can't. Because composite materials, they behave differently. And the failure mechanisms are totally different from metals.
Sundar, I had a question on that particle, the striations on the particle which indicated the interfacial decohesion.
Yeah.
Does that mean there's some metal stuck to the surface of the particle? I mean, why are we seeing the particle itself? If it went through the particle, it would be a brittle failure. But this is happening at the interface and leaving some residue of some topographical feature. I mean, what is that coming from? Why am I seeing lines on a when there's no plasticity. Well, on the surface which has no plasticity. The other side of the fracture, the mating surface of the fracture surface would be the void from which the particle separated. Sundar, are you there?
I mean, his
I think we
video
lost.
seems to be frozen. Yeah.
Yeah, he's frozen. Yeah.
Sorry, Vikram, I lost you for a moment. Could you repeat that question, please?
So, in that picture of the particle, which you said had decohered from the matrix at that interface, the person actually looked for the void from which the particle had from the mating surface. Hello.
Can you hear me?
Now I can hear you.
Yeah. Yeah, you see, these are not they are not inclusions. They are secondary particulates of the same alloy in aluminum alloys.
My question was, I can understand that you see any kind of dimples or I'm sorry, striations that are characteristic of plasticity and topography that comes from plasticity during fatigue on the metal side of the fracture. But why do you see those features, those rings on the particle itself?
No, you don't see it on the particle. You see it on the surface of the void.
Okay, because I thought the particle itself also showed some, rings.
No. All the pictures were of on the particulates. There are no marks. The marks are always on the surface of the void.
I see. Okay.
Yeah, you're right. There's nothing on the particulate.
So I think there is a question, what is the standard method for measurement of fatigue crack growth rate? I think ASTM E647.
Right. Yeah.
So, yeah, if there are no further questions, I think I'll thank Dr. Sundar for his, well delved over the 4.5 decades of research, this domain, which he tried to kind of convey it in this 45 minutes of lecture. I don't think it's an easy task, but he tried to convey the ideas as much as we can understand. So we should thank him profusely for this. And this almost brings us to the end of this half-day workshop. Maybe if I request all the resource persons to kind of switch on the camera, then we will just. Yeah. So we have had 4 lectures. I don't know where is Baumik. We've had 4 lectures in the morning. The first 2 dealing with what is called as introduction to electron microscopy and getting into the the details of how high scale measurements are possible using the electron microscopy. The second lecture by Professor Shankaran talked about the use of TEM to understand the what I call the microstructural dynamics of what is happening during a fatigue test. So, I mean, that is very interesting. In fact, I wanted to check with him whether we can look at coupling it with other, non-destructive evaluation techniques.
Possible, yes.
To understand the dynamics of the failure. And the third lecture was kind of more on the practical applications of the, the failures which are understood through the electron microscopy. And the fourth lecture is on engineering a sequence fingerprint on the fracture surface, and from there understand the dynamics of crack growth for design purposes. So these 4 lectures were very, very elucidating in terms of the subject matter that is being covered. And having said this, if the resource persons would like to say a few words, I would like them to share their views and ideas on this.
Well,
can take-
I would just ask people who have attended this whether to give us some feedback on what they learned from here and whether they would